A very warm welcome to my channel. It is a profound pleasure to have you here today, as we embark on a journey not to a specific time or place in human history, but to the very origins of life itself. We are shifting our focus from the conflicts that have shaped nations to the silent, epic struggle that has shaped every living thing on our planet. Today, we open the pages of one of the most influential and revolutionary books ever written, Charles Darwin's On the Origin of Species. This is not merely a scientific textbook. It is a grand, sweeping narrative that forever changed our understanding of our place in the universe. Darwin invites us to become naturalists alongside him, to observe the intricate variations in the pigeons in a breeder's loft, to marvel at the perfectly adapted beak of a finch, and to contemplate the immense branching tree of life that connects us all. He asks us to consider a world in constant, gradual change, driven by a powerful yet simple mechanism, natural selection. In this full, unabridged reading, we will experience Darwin's arguments as he first laid them out. We will follow his meticulous observations, his carefully reasoned logic, and the sheer intellectual courage it took to propose a theory that challenged the core beliefs of his time. This is a story of struggle, of adaptation, and of the incredible diversity that has emerged from a few simple beginnings over countless eons. It's a detective story where the clues are found in the fossil record, in the geographical distribution of species, and in the very bones and tissues of living creatures. So, find a comfortable space, open your mind, and let us begin this extraordinary exploration into the grand view of life. Let us hear, in his own words, the theory that shook the world. When we look to the individuals of the same variety or subvariety of our older cultivated plants and animals, one of the first points which strikes us is that they generally differ more from each other than do the individuals of any one species or variety in a state of nature. When we reflect on the vast diversity of the plants and animals which have been cultivated, and which have varied during all ages under the most different climates and treatment, I think we are driven to conclude that this greater variability is simply due to our domestic productions having been raised under conditions of life not so uniform as, and somewhat different from, those to which the parent species have been exposed under nature. There is also, I think, some probability in the view propounded by Andrew Knight that this variability may be partly connected with excess of food. It seems pretty clear that organic beings must be exposed during several generations to new conditions to cause any great amount of variation, and that when the organization has once begun to vary, it generally continues to vary for many generations. No cases on record of a variable organism ceasing to vary under cultivation. Our oldest cultivated plants, such as wheat, still yield new varieties. Our oldest domesticated animals are still capable of rapid improvement or modification. As far as I am able to judge, after long attending to the subject, the conditions of life appear to act in two ways: directly on the whole organization or on certain parts alone, and indirectly by affecting the reproductive system. With respect to the direct action, we must bear in mind that in every case, as Professor Weissman has lately insisted, and as I have incidentally shown in my work on variation under domestication, there are two factors, namely the nature of the organism and the nature of the conditions. The former seems to be much the more important, for nearly similar variations sometimes arise under, as far as we can judge, dissimilar conditions, and on the other hand, dissimilar variations arise under conditions which appear to be nearly uniform. The effects on the offspring are either definite or indefinite. They may be considered as definite when all or nearly all the offspring of individuals exposed to certain conditions during several generations are modified in the same manner. It is extremely difficult to come to any conclusion in regard to the extent of the changes which have been thus definitely induced. There can, however, be little doubt about many slight changes, such as size from the amount of food, colour from the nature of the food, thickness of the skin and hair from climate, etc. Each of the endless variations which we see in the plumage of our fowls must have had some efficient cause, and if the same cause were to act uniformly during a long series of generations on many individuals, all probably would be modified in the same manner. Such facts as the complex and extraordinary outgrowths which invariably follow from the insertion of a minute drop of poison by a gall-producing insect show us what singular modifications might result in the case of plants from a chemical change in the nature of the sap. Indefinite variability is a much more common result of changed conditions than definite variability, and has probably played a more important part in the formation of our domestic races. We see indefinite variability in the endless slight peculiarities which distinguish the individuals of the same species, and which cannot be accounted for by inheritance from either parent or from some more remote ancestor. Even strongly marked differences occasionally appear in the offspring from the same parents, and in individuals of the same litter. There are instances of differences so strongly marked that they may be called monstrosities, but for my present purpose I shall confine myself to the more slight variations. These variations appear to be induced by the same general causes, and to obey the same laws as the more sudden and important modifications of structure which are occasionally developed in our domestic productions, and which are commonly called monstrosities. In regard to what I have called indefinite variability, occurring in single births, we are driven to conclude that this is the result of the conditions of life, of the same nature as those which act on the parents, acting on the embryo and germ, even up to that early period of development when the germ has not been fertilized. It appears that variability of this kind is also inherited, for otherwise there would be no ground for selection by man. He who sees his chicks vary must select, but he who sees no variation can select nothing. I shall now say a few words on the circumstances favourable to variation. It has been found in the case of our domestic animals that the most favourable circumstances are when they are crossed with other distinct stocks, but this does not apply to plants which have been long cultivated. It would seem that the change in the conditions of life, whatever it may be, is the fundamental cause of the variation. In the case of animals, the most favourable circumstances for variation are when they are bred under confinement and are plentifully supplied with food. In the case of plants, the evidence is not so clear, but when they are cultivated in rich soil and are protected from the competition of other plants, they seem to vary most. We may infer that changed habits produce an inherited effect. For instance, the changed period of flowering in plants when transported from one climate to another. In animals, the increased use or disuse of parts has had a more marked influence. Thus I find in the domestic duck that the bones of the wing weigh less and the bones of the leg more, in proportion to the whole skeleton, than do the same bones in the wild duck, and this change may be safely attributed to the domestic duck flying much less and walking more than its wild parents. The great and inherited development of the udders in cows and goats in countries where they are habitually milked, in comparison with these organs in other countries, is another instance of the effect of use. Not one of our domestic animals can be named which has not in some country drooping ears, and the view which has been suggested that the drooping is due to the disuse of the muscles of the ear, from the animals being seldom much alarmed, seems probable. There are many laws regulating variation, some few of which can be dimly seen and will hereafter be briefly discussed. I will here only allude to what may be called correlation of growth. Any change in the embryo or larva will almost certainly entail changes in the mature animal. In monstrosities, the correlations between quite distinct parts are very curious, and many instances are given in Isidore Geoffroy Saint-Hilaire's great work on this subject. Breeders believe that long limbs are almost always accompanied by an elongated head. Some instances of correlation are quite whimsical. Thus cats which are entirely white and have blue eyes are generally deaf, but it has been lately stated by Mr. Tate that this is confined to the males. Colour and constitutional peculiarities go together, of which many remarkable cases could be given amongst animals and plants. From facts collected by Hosinger, it appears that white sheep and pigs are poisoned by certain plants, whilst dark-coloured individuals escape. Professor Wyman has recently communicated to me a good illustration of this fact, on asking some farmers in Virginia how it was that all their pigs were black. They informed him that the pigs ate the paint root lacnanthes, which coloured their bones pink, and which killed the white pigs but not the black ones. I will not enter on the detail of the evidence which proves that our domestic races have descended from, or are co-descendants with, other species. To do so would be to write a treatise on each of our domestic animals and cultivated plants, but I may state that I have, in my own work on this subject, collected a large number of facts which show that our domestic animals and cultivated plants have varied in a very remarkable manner, and that they have, with the exception of a few cases, been derived from a single species. It is clear that the diversity of the races of any one species is in some cases very great. For instance, the diversity of the races of the pigeon is something astonishing. Compare the English carrier and the short-faced tumbler and see the wonderful difference in their beaks, entailing corresponding differences in their skulls. The carrier, more especially the male bird, is also remarkable from the wonderful development of the carunculated skin about the head, and it is accompanied by greatly elongated eyelids, very large external orifices to the nostrils, and a wide gape of mouth. The short-faced tumbler has a beak in outline almost like that of a finch, and the common tumbler has the singular and strictly inherited habit of flying at a great height in a compact flock, and tumbling in the air head over heels. The runt is a bird of great size with long massive beak and large feet. Some of the sub-races of runts have very long necks, others very long wings and tails, others singularly short tails. The barb is allied to the carrier, but instead of a very long beak has a very short and broad one. The pouter has a much elongated body, wings and legs, and its enormously developed crop, which it glories in inflating, may well excite astonishment and even laughter. The turbit has a short and conical beak, with a line of reversed feathers down the breast, and it has the habit of continually expanding slightly the upper part of the esophagus. The Jacobin has the feathers so much reversed along the back of the neck that they form a hood, and it has, proportionally to its size, much elongated wing and tail feathers. The trumpeter and laugher, as their names express, utter a very different coo from the other breeds. The fantail has 30 or even 40 tail feathers, instead of 12 or 14, the normal number in all members of the great pigeon family, and these feathers are kept expanded and are carried so erect that in good birds the head and tail touch, the oil gland is quite aborted. Several other less distinct breeds might have been specified. In the skeletons of the several breeds, the development of the bones of the face in length and breadth and curvature differs enormously. The shape, as well as the breadth and length of the ramus of the lower jaw, varies in a highly remarkable manner. The number of the caudal and sacral vertebrae vary, as does the number of the ribs, together with their relative breadth and the presence of processes. The size and shape of the apertures in the sternum are highly variable, so is the degree of divergence and relative size of the two arms of the furcula, the proportional width of the gape of mouth, the proportional length of the eyelids, of the orifice of the nostrils, of the tongue, not always in strict correlation with the length of beak, the size of the crop, and of the upper part of the esophagus, the development and abortion of the oil gland, the number of the primary wing and caudal feathers, the relative length of wing and tail to each other and to the body, the relative length of leg and of the feet, the number of scutellae on the toes, the development of skin between the toes, are all points of structure which are variable. The period at which the perfect plumage is acquired varies, as does the state of the down with which the nestling birds are clothed when hatched. The shape and size of the eggs vary. The manner of flight differs remarkably, as does in some breeds the voice and disposition. Lastly, in certain breeds the males and females have come to differ to a slight degree from each other. Altogether at least a score of pigeons might be chosen, which if shown to an ornithologist, and he were told that they were wild birds, would certainly be ranked by him as well-defined species. Moreover, I do not believe that any ornithologist would place the English carrier, the short-faced tumbler, the runt, the barb, pouter, and fantail in the same genus, more especially as in each of these breeds several truly inherited sub-breeds or species, as he might have called them, could be shown him. Great as the differences are between the breeds of the pigeon, I am fully convinced that the common opinion of naturalists is correct, namely that all have descended from the rock pigeon, Columba livia, including under this term several geographical races or subspecies, which differ from each other in the most trifling respects. As several of the reasons which have led me to this belief are in some degree applicable in other cases, I will here briefly give them. If the several breeds are not varieties, and have not proceeded from the rock pigeon, they must have descended from at least 7 or 8 aboriginal stocks, for it is impossible to make the present domestic breeds by the crossing of any lesser number. How, for instance, could a pewter be produced by crossing 2 breeds unless one of the parent stocks possessed the characteristic enormous crop? the supposed aboriginal stocks must all have been rock pigeons, that is, not breeding or willingly perching on trees. But besides columbolivia with its geographical subspecies, only 2 or 3 other species of rock pigeons are known, and these have not any of the characters of the domestic breeds. Hence, the supposed aboriginal stocks must either still exist in the countries where they were originally domesticated, and yet be unknown to ornithologists, and this, considering their size, habits, and remarkable characters, seems very improbable, or they must have become extinct in the wild state. But birds breeding on precipices and good flyers are unlikely to be exterminated, and the common rock pigeon, which has the same habits with the domestic breeds, has not been exterminated even on several of the smaller British islets or on the shores of the Mediterranean. Hence, the supposed extermination of so many species having similar habits with the rock pigeon seems to me a very rash assumption. Moreover, the several above-named domesticated breeds have been transported to all parts of the world, and therefore some of them must have been carried back to their native country, but not one has ever become wild or feral, though the dovecot pigeon, which is the rock pigeon in a very slightly altered state, has become feral in several places. Again, all recent experience shows that it is difficult to get any wild animal to breed freely under domestication, yet on the hypothesis of the multiple origin of our pigeons, it must be assumed that at least 7 or 8 species were so thoroughly domesticated in ancient times by half-civilized man as to be quite prolific under confinement. An argument of great weight, and applicable in several other cases, is that the above-specified breeds, though agreeing generally in constitution, habits, voice, colouring, and in most parts of their structure, with the wild rock pigeon, yet are certainly highly abnormal in other parts of their structure. We may look in vain throughout the whole great family of Columbidae for a beak like that of the English carrier, or that of the short-faced tumbler, or a crop like that of the pouter, or tail feathers like those of the fantail. Hence, it must be assumed not only that half-civilized man succeeded in thoroughly domesticating several species, but that he intentionally, or by chance, picked out extraordinarily abnormal species, and further, that these very species have since all become extinct or unknown. So many strange contingencies seem to me improbable in the highest degree. Some facts in regard to the colouring of pigeons are important. The rock pigeon is of a slaty blue, and has a white rump. The Indian subspecies C. intermedia of Strickland having it bluish. The tail has a terminal dark bar, with the outer feathers externally edged at the base with white. The wings have 2 black bars. Some semi-domestic breeds, and some apparently truly wild breeds, have besides the 2 black bars, the wings checkered with black. These several marks do not occur together in any other species of the whole family. Now, in every one of the domestic breeds, taking thoroughly well-bred birds, all the above marks, even to the white edging of the outer tail feathers, sometimes concur perfectly developed. Moreover, when 2 birds belonging to 2 distinct breeds are crossed, neither of which is blue or has any of the above-specified marks, the mongrel offspring are very apt suddenly to acquire these characters. For instance, I crossed some uniformly white fantails with some uniformly black barbs, and they produced mottled brown and black birds. These I again crossed together, and one grandchild of the pure white fantail and pure black barb was of as beautiful a blue colour, with the white rump, double black wing bar, and barred and white-edged tail feathers, as any wild rock pigeon. We can understand these facts on the well-known principle of reversion to ancestral characters, if all the domestic breeds have descended from the rock pigeon, but if we deny this, we must make one of the 2 following highly improbable suppositions. Either first that all the several imagined aboriginal stocks were coloured and marked like the rock pigeon, although no other existing species is thus coloured and marked, so that in each separate breed there might be a tendency to revert to the very same colours and markings. Or, secondly, that each breed, even the purest, has within a dozen or at most within a score of generations been crossed by the rock pigeon. I say within a dozen or 20 generations, for we know of no fact countenancing the belief that the child ever reverts to some one ancestor, removed by a greater number of generations. In a breed which has been crossed only once with some distinct breed, the tendency to reversion to any character derived from such cross will naturally become less and less, as in each succeeding generation there will be less of the foreign blood. But when there has been no cross with a distinct breed, and there is a tendency in both parents to revert to a character which has been lost during some former generation, this tendency, for all that we can see to the contrary, may be transmitted undiminished for an indefinite number of generations. These two distinct cases are often confounded in treatises on inheritance. Lastly, the hybrids or mongrels from between all the domestic breeds of the pigeon are perfectly fertile. I can state this from my own observations, purposely made on the most distinct breeds. Now, it is difficult, perhaps impossible, to bring forward one case of the hybrid offspring of two animals, clearly distinct, being themselves perfectly fertile. Some authors believe that long-continued domestication eliminates this strong tendency to sterility from the history of the dog and of some other domestic animals. This conclusion is probably quite correct if applied to species closely related to each other, but to extend it so far as to suppose that species differing to the great extent that the carrier and tumbler do from each other, or that the fantail and pouter do from each other, would be rash in the extreme, from these several reasons, namely, the improbability of man having formerly got 7 or 8 supposed species of pigeons to breed freely under domestication, these supposed species being quite unknown in a wild state, and then not having become anywhere feral, these species having certain very abnormal characters in certain breeds, yet leaving nearly all their other characters untouched, so that they resemble the rock pigeon in the minutest details, the occasional reappearance of the blue colour and various black marks in all the breeds, both when kept pure and when crossed, and lastly the mongrel offspring being perfectly fertile. From these several reasons taken together, we may safely conclude that all our domestic breeds are descended from the rock pigeon or Columba livia with its geographical subspecies. In favour of this view I may add, firstly, that the wild Cis livia has been found capable of domestication in Europe and in India, and that it agrees in habits and in a great number of points of structure with all the domestic breeds. Secondly, that although an English carrier or a short-faced tumbler differs immensely in certain characters from the rock pigeon, yet that by comparing the several sub-breeds of these breeds, more especially those brought from distant countries, we can make an almost perfect series between the extremes of structure. Thirdly, those characters which are mainly distinctive of each breed are in each eminently variable. For instance, the wattle and length of beak of the carrier, the shortness of that of the tumbler, and the number of tail feathers in the fantail, and the explanation of this fact will be obvious when we treat of selection. Fourthly, pigeons have been watched and tended with the utmost care, and loved by many people. They have been domesticated for thousands of years in several quarters of the world. The earliest known record of pigeons is in the 5th Egyptian dynasty, about 3000 BC, as was pointed out to me by Professor Lepsius, but Mr. Birch informs me that pigeons are given in a bill of fare in the previous dynasty. In the time of the Romans, as we hear from Pliny, immense prices were given for pigeons. Nay, they are come to this pass that they can reckon up their pedigree and race. Pigeons were much valued by Akbar Khan in India, about the year 1600. Never less than 20,000 pigeons were taken with the court. The monarchs of Iran and Turan sent him some very rare birds, and continues the courtly historian, His Majesty, by crossing the breeds, which method was never practiced before, has improved them astonishingly. About this same period the Dutch were as eager about pigeons as were the old Romans. The paramount importance of these considerations in explaining the immense amount of variation which pigeons have undergone will likewise be obvious when we treat of selection. We shall then also see how it is that the breeds so often have a somewhat monstrous character. It is also a most favourable circumstance for the production of distinct breeds, that male and female pigeons can be easily mated for life, and thus different breeds can be kept together in the same aviary. I have discussed the probable origin of domestic pigeons at some yet quite insufficient length, because when I first kept pigeons and watched the several kinds, knowing well how true they bred, I felt fully as much difficulty in believing that since they were domesticated, they had all proceeded from a common parent, as any naturalist could in coming to a similar conclusion in regard to the many species of finches or other groups of birds in nature. One circumstance has struck me much, namely that nearly all the breeders of the various domestic animals and the cultivators of plants with whom I have ever conversed or whose treatises I have read, are firmly convinced that the several breeds to which each has attended are descended from so many aboriginal species. Ask, as I have asked, a celebrated raiser of Hereford cattle, whether his cattle might not have descended from longhorns, and he will laugh you to scorn. I have never met a pigeon or poultry or duck or rabbit fancier who was not fully convinced that each main breed was descended from a distinct species. Van Mons, in his treatise on pears and apples, shows how utterly he disbelieves that the several sorts, for instance a Ribston pippin or a Codlin apple, could ever have proceeded from the seeds of the same tree. Innumerable other examples could be given. The explanation, I think, is simple. From long-continued study, they are strongly impressed with the differences between the several races, and though they well know that each race varies slightly, for they win their prizes by selecting such slight differences, yet they ignore all general arguments and refuse to sum up in their minds slight differences accumulated during many successive generations. May not those naturalists who, knowing far less of the laws of inheritance than does the breeder, and knowing no more than he does of the intermediate links in the long lines of descent, yet admit that many of our domestic races are descended from the same parents, may they not learn a lesson of caution when they deride the idea of species in a state of nature being lineal descendants of other species? Let us now briefly consider the steps by which domestic races have been produced, either from one or from several allied species. Some effect may be attributed to the direct and definite action of the external conditions of life, and some to habit, but he would be a bold man who would account by such agencies for the differences between a dray and a race-horse, a greyhound and a bloodhound, a carrier and a tumbler pigeon. One of the most remarkable features in our domesticated races is that we see in them adaptation, not indeed to the animal's or plant's own good, but to man's use or fancy. Some variations useful to him have probably arisen suddenly, or by one step. Many botanists, for instance, believe that the fuller's tea-easel with its hooks, which cannot be rivalled by any mechanical contrivance, is only a variety of the wild dipsacus, and this amount of change may have suddenly arisen in a seedling. So it has probably been with the turnspit dog, and this is known to have been the case with the Ancon sheep. But when we compare the dray horse and racehorse, the dromedary and camel, the various breeds of sheep fitted either for cultivated land or mountain pasture, with the wool of one breed good for one purpose, and that of another breed for another purpose. When we compare the many breeds of dogs, each good for man in different ways, when we compare the gamecock so pertinacious in battle with other breeds so little quarrelsome, with everlasting layers which never desire to sit, and with the bantam so small and elegant, when we compare the host of agricultural, culinary, horticultural and florists' products, varying so greatly in fruit, foliage, flower and tuber or root, we must, I think, look further than to mere variability. We cannot suppose that all the breeds were suddenly produced as perfect and as useful as we now see them. Indeed, in many cases we know that this has not been their history. The key is man's power of accumulative selection. Nature gives successive variations. Man adds them up in certain directions useful to him. In this sense he may be said to have made for himself useful breeds. The great power of this principle of selection is not hypothetical. It is certain that several of our eminent breeders have, even within a single lifetime, modified to a large extent their breeds of cattle and sheep. In order to fully realize what they have done, it is almost necessary to read several of the many treatises devoted to this subject, and to inspect the animals. Breeders habitually speak of an animal's organization as something plastic, which they can model almost as they please. If I had space, I could quote numerous passages to this effect from highly competent authorities. Youatt, who was probably better acquainted with the works of agriculturalists than almost any other individual, and who was himself a very good judge of animals, speaks of the principle of selection as that which enables the agriculturist not only to modify the character of his flock, but to change it altogether. It is the magician's wand, by means of which he may summon into life whatever form and mould he pleases. Lord Somerville, speaking of what breeders have done for sheep, says, "It would seem as if they had chalked out upon a wall a form perfect in itself, and then had given it existence." In Saxony, the importance of the principle of selection in regard to merino sheep is so fully recognized that men follow it as a trade. The sheep are placed on a table and are studied, like a picture by a connoisseur. This is done 3 times at intervals of months, and the sheep are each time marked and classed, so that the very best may be selected for breeding. What English breeders have actually effected is proved by the enormous prices given for animals with a good pedigree, and these have been exported to almost every quarter of the world. The same principles are followed by horticulturists, but the variations are here often more abrupt. No one supposes that our choicest productions have been produced by a single variation from the aboriginal stock. We have proofs that this is not so in some cases in which exact records have been kept. Thus, to give a very trifling instance, the steadily increasing size of the common gooseberry may be quoted. We see an astonishing improvement in many florists' flowers, when the flowers of the present day are compared with drawings made only 20 or 30 years ago. When a race of plants is once pretty well established, the seed raisers do not pick out the best plants, but merely go over their seed beds and pull up the rogues, as they call the plants that deviate from the proper standard. With animals, this kind of selection is in fact likewise followed, for hardly anyone is so careless as to breed from his worst animals. In regard to plants, there is another means of observing the accumulated effects of selection, namely by comparing the diversity of flowers in the different varieties of the same species in the flower garden. The diversity of leaves, pods or tubers or whatever part is valued in the kitchen garden in comparison with the flowers of the same varieties, and the diversity of fruit of the same species in the orchard in comparison with the leaves and flowers of the same set of varieties. See how different the leaves of the cabbage are, and how extremely alike the flowers, how unlike the flowers of the heartsease are, and how alike the leaves, how much the fruit of the different kinds of gooseberries differ in size, colour, shape, and hairiness, and yet the flowers present very slight differences. It is not that the varieties which differ largely in some one point do not differ at all in other points. This is hardly ever, I speak after careful observation, perhaps never the case. The law of correlated variation, the importance of which should never be overlooked, will ensure some differences, but as a general rule, it cannot be doubted that the continued selection of slight variations, either in the leaves, the flowers, or the fruit, will produce races differing from each other chiefly in these characters. It may be objected that the principle of selection has been reduced to methodical practice for scarcely more than 3/4 of a century. It has certainly been more attended to of late years, and many treatises have been published on the subject, and the result has been, in a corresponding degree, rapid and important. But it is very far from true that the principle is a modern discovery. I could give good evidence that the principle was followed unintentionally in ancient times. In rude and barbarous periods of English history choice, animals were often imported and laws were passed to prevent their exportation. The destruction of horses under a certain size was ordered, and this may be compared to the roguing of plants by nurserymen. The principle of selection I find distinctly given in an ancient Chinese encyclopedia. Explicit rules are laid down by some of the Roman classical writers. From passages in Genesis, it is clear that the colour of domestic animals was at that early period attended to. Savages now sometimes cross their dogs with wild canine animals to improve the breed, and they formerly did so, as is attested by passages in Pliny. The savages in South Africa match their draught cattle by colour, as do some of the Esquimaux their teams of dogs. Livingstone states that good domestic breeds are highly valued by the Negroes in the interior of Africa who have not associated with Europeans. Some of these facts do not show actual selection, but they show that the breeding of domestic animals was carefully attended to in ancient times and is now attended to by the lowest savages. It would indeed have been a strange fact had attention not been paid to breeding, for the inheritance of good and bad qualities is so obvious. At the present time, eminent breeders try by methodical selection with a distinct object in view to make a new strain or subbreed superior to anything of the kind in the country. But, for our purpose, a form of selection which may be called unconscious, and which results from everyone trying to possess and breed from the best individual animals, is more important. Thus, a man who intends keeping pointers naturally tries to get as good dogs as he can, and afterwards breeds from his own best dogs, but he has no wish or expectation of permanently altering the breed. Nevertheless, we may infer that this process continued during centuries, would improve and modify any breed in the same way as Bakewell, Collins, etc. By this very same process, only carried on more methodically, did greatly modify even during their lifetimes the forms and qualities of their cattle. Slow and insensible changes of this kind could never be recognized unless actual measurements or careful drawings of the breeds in question had been made long ago, which might serve for comparison. In some cases, however, unchanged or but little changed individuals of the same breed exist in less civilized districts, where the breed has been less improved. There is reason to believe that King Charles's Spaniel has been unconsciously modified to a large extent since the time of that monarch. Some highly competent authorities are convinced that the setter is directly derived from the hound, and has probably been slowly altered from it. It is known that the English pointer has been greatly changed within the last century, and in this case the change has, it is believed, been chiefly affected by crosses with the foxhound. But what concerns us is that the change has been effected unconsciously and gradually, and yet so effectually, that though the old Spanish pointer certainly came from Spain, Mr. Borrow has not seen, as I am informed by him, any native dog in Spain like our pointer. By a similar process of selection and by careful training, English racehorses have come to surpass in speed and size the parent Arabs, so that the latter, by the rules for the Goodwood Cup, are favoured in the weights which they carry. Lord Spencer and others have shown how the cattle of England have increased in weight and in early maturity, compared with the stock formerly kept in this country. By comparing the accounts given in various old treatises of the former and present state of carrier and tumbler pigeons in Britain, India, and Persia, we can trace the stages through which they have insensibly passed, and come to differ so greatly from the rock pigeon. Ewart gives an excellent illustration of the effects of a course of selection, which may be considered as unconscious, in so far that the breeders could never have expected, or even wished, to produce the result which ensued, namely, the production of two distinct strains. The two flocks of Leicester sheep kept by Mr. Buckley and Mr. Burgess have been purely bred from the original stock of Mr. Bakewell for upwards of 50 years. There is not a suspicion existing in the mind of anyone at all acquainted with the subject, that the owner of either of them has deviated in any one instance from the pure blood of Mr. Bakewell's flock, and yet the difference between the sheep possessed by these two gentlemen is so great that they have the appearance of being quite different varieties. If there exist savages so barbarous as never to think of the inherited character of the offspring of their domestic animals, yet any one animal particularly useful to them, for any special purpose, would be carefully preserved during famines and other accidents, to which savages are so liable, and such choice animals would thus generally leave more offspring than the inferior ones, so that in this case there would be a kind of unconscious selection going on. We see the value set on animals even by the barbarians of Tierra del Fuego, by their killing and devouring their old women, in times of dearth, as of less value than their dogs. It implants the same gradual process of improvement, through the occasional preservation of the best individuals, whether or not sufficiently distinct to be ranked at their first appearance as distinct varieties, and whether or not two or more species or races have become blended together by crossing, may plainly be recognized in the increased size and beauty which we now see in the varieties of the heartsease, rose, pelargonium, dahlia, and other plants, when compared with the older varieties or with their parent stocks. No one would ever expect to get a first-rate heartsease or dahlia from the seed of a wild plant. No one would expect to raise a first-rate melting pear from the seed of the wild pear, though he might succeed from a poor seedling growing wild, if it had come from a garden stock. The pear, though cultivated in classical times, appears, from Pliny's description, to have been a fruit of very inferior quality. I have seen great surprise expressed in horticultural works at the wonderful skill of gardeners in having produced such splendid results from such poor materials, but the art has been simple, and as far as the final result is concerned, has been followed almost unconsciously. It has consisted in always cultivating the best-known variety, sowing its seeds, and when a slightly better variety chanced to appear, selecting it, and so onwards. But the gardeners of the classical period, who cultivated the best pears which they could procure, never thought what splendid fruit we should eat, though we owe our excellent fruit in some small degree to their having naturally chosen and preserved the best varieties they could anywhere find. A large amount of change, thus slowly and unconsciously accumulated, explains, as I believe, the well-known fact that in a number of cases we cannot recognize and therefore do not know the wild parent stocks of the plants which have been longest cultivated in our flower and kitchen gardens. If it has taken centuries or thousands of years to improve or modify most of our plants up to their present standard of usefulness to man, we can understand how it is that neither Australia, the Cape of Good Hope, nor any other region inhabited by quite uncivilized man has afforded us a single plant worth culture. It is not that these countries, so rich in species, do not by a strange chance possess the aboriginal stocks of any useful plants, but that the native plants have not been improved by continued selection up to a standard of perfection comparable with that acquired by the plants in countries anciently civilized. In regard to the domestic animals kept by uncivilized man, it should not be overlooked that they almost always have to struggle for their own food, at least during certain seasons. And in two countries very differently circumstanced, individuals of the same species having slightly different constitutions or structure would often succeed better in the one country than in the other, and thus by a process of natural selection, as will hereafter be more fully explained, two subbreeds might be formed. This perhaps partly explains what has been remarked by some authors, namely, that the varieties kept by savages have more of the character of species than the varieties kept in civilized countries. On the view here given of the important part which selection has played, it becomes at once obvious how it is that our domestic races show adaptation in their structure or in their habits to man's wants or fancies. We can, I think, further understand the frequently abnormal character of our domestic races, and likewise their differences being so great in external characters and relatively so slight in internal parts or organs. Man can hardly select, or only with much difficulty, any deviation of structure excepting such as is externally visible, and indeed he rarely cares for what is internal. He can never act by selection excepting on variations which are first given to him in some slight degree by nature. No man would ever try to make a fantail till he saw a pigeon with a tail developed in some slight degree in an unusual manner, or a pouter till he saw a pigeon with a crop of unusual size, and the more abnormal or unusual any character was when it first appeared, the more likely it would be to catch his attention. But to use such an expression as trying to make a fantail is, I have no doubt, in most cases utterly incorrect. The man who first selected a pigeon with a slightly larger tail never dreamed what the descendants of that pigeon would become through long-continued, partly unconscious and partly methodical selection. Perhaps the parent bird of all fantails had only 14 tail feathers somewhat expanded like the present Java fantail, or like individuals of other and distinct breeds, in which as many as 17 tail feathers have been counted. Perhaps the first pouter pigeon did not inflate its crop much more than the turbit now does the upper part of its esophagus, a habit which is disregarded by all fanciers, as it is not one of the points of the breed. Nor let it be thought that some great deviation of structure would be necessary to catch the fancier's eye. He perceives extremely small differences, and it is in human nature to value any novelty, however slight, in one's own possession. Nor must the value which would formerly have been set on any slight differences in the individuals of the same species be judged of by the value which is now set on them, after several breeds have fairly been established. It is known that with pigeons many slight variations now occur, but these are rejected as faults or deviations from the standard of perfection in each breed. The common goose has not given rise to any marked varieties, hence the Toulouse and the common breed, which differ only in colour, that most fleeting of characters have lately been exhibited as distinct at our poultry shows. These views appear to explain what has sometimes been noticed, namely, that we know hardly anything about the origin or history of any of our domestic breeds, but in fact, a breed, like a dialect of a language, can hardly be said to have a distinct origin. A man preserves and breeds from an individual with some slight deviation of structure, or takes more care than usual in matching his best animals, and thus improves them, and the improved animals slowly spread in the immediate neighbourhood. But they will as yet hardly have a distinct name, and from being only slightly valued, their history will have been disregarded. When further improved by the same slow and gradual process, they will spread more widely, and will be recognized as something distinct and valuable, and will then probably first receive a provincial name. In semi-civilized countries with little intercommunication, the breeding of a local race having thus begun, spreads slowly, and may in time form a distinct stock. But the frequent process of crossing with other races will blend the characters of the two breeds, and so obscure their origin. And lastly, a man who cares little for tracing the pedigree of his animals, sells his surplus stock to any purchaser, who takes them to a distant country and there speaks of his own new breed as originated in his own district. I believe that something of this kind has occurred with our dogs, and that all our domestic races are descended from 2 or 3 wild species which have been modified by crossing and by selection, and that this process has been going on from the most remote antiquity. In this case, it is not likely that the aboriginal stocks would still exist in a pure state. I believe that this process of selection has been the great agency in the formation of our domestic breeds, the child of man's art, working upon the materials given him by nature. But I am convinced that it has been a slow and insensible process, and that its effects have been great only after a long series of years. Nor am I so foolish as to imagine that I have exhausted the subject of the origin of our domestic races. A great deal more remains to be done, as will be seen in my larger work. To sum up on the origin of our domestic races, I believe that the conditions of life from their action on the reproductive system are so far of the highest importance as causing variability. I do not believe that variability is an inherent and necessary contingency under all circumstances with all organic beings, as some authors have thought. The effects of variability are modified by inheritance and reversion. Selection is the prepotent power, whether applied methodically and more quickly, or unconsciously and more slowly but more efficiently. I should never have studied the subject of the origin of species, had not the study of domesticated animals opened my eyes to the vast power of man's selection. Let us now turn to the variability of organisms in a state of nature. Before applying the principles arrived at in the last chapter to organic beings in a state of nature, we must briefly discuss whether these latter are subject to any variation. To treat this subject properly, a long catalogue of dry facts ought to be given, but these I shall reserve for a future work. Nor shall I here discuss the various definitions which have been given of the term species. No one definition has satisfied all naturalists, yet every naturalist knows vaguely what he means when he speaks of a species. Generally, the term includes the unknown element of a distinct act of creation. The term variety is almost equally difficult to define, but here community of descent is almost universally implied, though it can rarely be proved. We have also what are called monstrosities, but they graduate into varieties by imperceptible steps. By a monstrosity, I presume, is meant some considerable deviation of structure, generally injurious or not useful to the species. Some authors use the term variation in a technical sense as implying a modification directly due to the physical conditions of life, and variations in this sense are supposed not to be inherited. But who can say that the dwarfed condition of shells in the brackish waters of the Baltic, or dwarfed plants on alpine summits, or the thicker fur of an animal from far northwards, would not in some cases be inherited for at least a few generations, and in this case I presume that the form would be called a variety. It may be doubted whether sudden and considerable deviations of structure, such as we occasionally see in our domestic productions, more especially with plants, are ever permanently propagated in a state of nature. Almost every part of every organic being is so beautifully related to its complex conditions of life that it seems as improbable that any part should have been suddenly produced perfect, as that a complex machine should have been invented perfect. Under domestication, monstrosities sometimes occur which resemble normal structures in widely different animals. Thus, pigs have occasionally been born with a sort of proboscis, and if any wild species of the same genus had naturally possessed a proboscis, it might have been argued that this had appeared as a monstrosity, but I have as yet failed to find, after diligent search, cases of monstrosities resembling normal structures in nearly allied forms, and these alone bear on the question. If monstrous forms of this kind ever do appear in a state of nature and are capable of reproduction, which is not always the case, as they occur rarely and singly, their preservation would depend on unusually favourable circumstances. They would also, during the first and succeeding generations, cross with the ordinary form, and thus their abnormal character would almost inevitably be lost. But I shall have to return in a future chapter to the preservation and perpetuation of single or occasional variations, independently of the direct effects of the conditions of life and of the occasional appearance of sudden modifications of structure. There is in all organized beings a tendency to vary, which is probably connected with their conditions of life, and especially with their reproductive system. This tendency is likewise inherited, for, as we have seen in the first chapter, the variation of our domestic productions is by no means confined to the first generation. This inherited tendency to vary is what we have to consider in regard to organisms in a state of nature. Individual differences, as they are called, are of the highest importance for us, for they are often inherited, as must be familiar to every one, and they thus afford materials for natural selection to act on and accumulate, in the same manner as man accumulates in any given direction, individual differences in his domesticated productions. These individual differences are of the highest importance for us, as they are the first steps towards such slight varieties as are barely thought worth recording in works on natural history, and I have evidence to show that there is no fundamental distinction between individual differences and the slighter varieties of the same species. I could give a long catalogue of facts showing that the same parts of the same individual and the same parts of different individuals are liable to the same kind of variation. Thus the same colours and markings are apt to reappear in the individuals of the same species and in the varieties of the same species. The same parts are liable to become united or to be multiplied. In plants, the same parts are liable to become petaloid. In insects, the same parts are liable to become antenna-formed. Such facts are of high importance, but I must reserve them for my future work. Before treating of the varieties of species, it may be worthwhile to say a few words on the species themselves. I must premise that I do not suppose that all species are equally variable. One species varies more than another. Thus, to take one instance from a single family of plants, the species of the genus Pelargonium vary much more than those of the genus Erodium. But if we look to our domestic productions, we find that some species have varied more than others. Thus the pigeon has varied much more than the goose. Now if some of our domestic productions are not varieties of aboriginal species, but are themselves aboriginal species, this would show that some species are more liable to vary than others. Those who have given most attention to the subject of species are the very men who are most perplexed by the attempt to limit them. This may be seen by consulting the works of any of our greatest botanists. Thus Mr. H.C. Fox Watson, to whom I lie under deep obligation for assistance of all kinds, has marked for me in the well-sifted London Catalogue of Plants, 4th edition, 1802 British plants, which are generally considered as varieties, but which have all been ranked by some botanists as species, and in this list of 182, some of the most able botanists in this country are recorded as believing them to be good and true species. Mr. Watson also has sent me a still more remarkable list of 130 British plants, which are now ranked as species, but which he considers are so closely allied to other species, or to each other, that he thinks it probable that they will hereafter be united. And Mr. Babington, who has carefully studied our British plants, with a view to their specific limits, writes me that he finds that there are many plants which he cannot determine whether to rank as species or as varieties. Mr. Wallace, in his admirable paper on the geographical distribution of animals, has expressed his belief that the individuals of the same species inhabiting the same country vary more than those inhabiting different countries. And this is probably true, for the individuals inhabiting the same country are more exposed to the same conditions of life. But I must add that I think I have seen evidence that the same species varies in the same manner in different countries. For instance, in going over the collections of birds from different parts of the world, I have been struck with the fact that I have frequently seen in the same species the same slight variations of plumage in birds from the most distant countries. When we come to the study of any one group of animals or plants, we shall find that some species are common and widely ranged, and that others are rare and have a narrow range. We shall find that some of the common species are very variable, and that others are not so. On the other hand, some of the rare species are very variable, and others are not so. There is some reason to believe that the common and widely ranged species are more variable than the rare and restricted species, I have tabulated the results of my inquiries on this subject, and they seem to me to show that this is the case, but I must add that my materials are very imperfect. I will here only give one instance from a large family of plants, the Compositae. I find that out of 387 species of this family which are found in Great Britain, 25 are common and widely ranged, and that of these 25, 17 are very variable. On the other hand, out of the remaining 362 species which are either rare or have a restricted range, only 14 are very variable. On the theory for which I am contending, the common and widely ranged species which have already beaten their competitors in their own country, and which have already spread into other countries, would be the most likely to give rise to new varieties or incipient species, and this they would do by still further increasing in numbers, and by still further extending their range. I do not mean to say that all common and widely ranged species are now varying. On the contrary, I believe that some of them are now stationary in character, but I believe that the common and widely ranged species are those which have varied most in past times, and which are now most likely to vary again. I think it will be found to be the general rule that wherever many species of a genus have been formed in any country, the species of that genus present a greater number of varieties, that is, of incipient species, than do the species of a genus having few species in the same country. This may be seen by taking any catalogue of plants or insects. Thus, in Great Britain, the species of large genera such as Rosa, Rubus and Hieracium are very variable. On the other hand, the species of small genera such as Linnea are not so. I will here give one instance from the British insects. I find that out of 2,426 species of Coleoptera which are found in Great Britain, 1,237 belong to genera which contain more than 10 species, and that of these 1,237 species, 350 are very variable. On the other hand, out of the remaining 1,189 species, which belong to genera containing less than 10 species, only 60 are very variable. These facts are of plain signification on the view that species are only strongly marked and permanent varieties, for wherever many species of the same genus have been formed, or where, if we may use the expression, the manufactory of species has been active, we ought generally to find the manufactory still in action, more especially as we have every reason to believe the process of manufacturing new species to be a slow one, and this certainly is the case, if varieties be looked at as incipient species. For my tables clearly show as a general rule that wherever many species of a genus have been formed, the species of that genus present a number of varieties, that is, of incipient species, beyond the average. It is not that all large genera are now varying much and are thus increasing in the number of their species, or that no small genera are now varying and increasing, for if this had been so, it would have been fatal to my theory. Inasmuch as geology plainly tells us that small genera have in the lapse of time often increased greatly in size, and that large genera have often come to their maxima, declined and disappeared. All that we want to show is that where many species of a genus have been formed, on an average many are still forming, and this certainly holds good. There are other relations between the species of large genera and their recorded varieties which are curious. We have seen that there is no infallible criterion by which to distinguish species, and well-marked varieties, and when intermediate links have not been found between doubtful forms, naturalists are compelled to come to a determination by the amount of difference between them, judging by analogy whether or not the amount suffices to raise one or both to the rank of species. Hence, the amount of difference is one very important criterion in settling whether two forms should be ranked as species or varieties. Now, Frieds has remarked in regard to plants and Westwood in regard to insects, that in large genera the amount of difference between the species is often exceedingly small. I have endeavoured to test this numerically by averages, and as far as my imperfect results go, they confirm this remark. I have also consulted some sagacious and experienced observers, and after reflection they concur in this view. In this respect, therefore, the species of large genera resemble varieties, more than do the species of small genera, or the case may be put in another way, and it may be said that in large genera, in which a number of varieties or incipient species greater than the average are now manufacturing, many of the species already manufactured still to a certain extent resemble varieties. for they differ from each other by a less than the usual amount of difference. Moreover, the species of large genera are related to each other in the same manner as the varieties of any one species are related to each other. No naturalist pretends that all the species of a genus are equally distinct from each other. They may generally be divided into subgenera or sections or lesser groups. As Fries has well remarked, little groups of species are generally clustered like satellites around other species. And what are varieties but groups of forms unequally related to each other and clustered round their parent species? Undoubtedly there is one most important point of difference between varieties and species, namely that the amount of difference between varieties when compared with each other or with their parent species is much less than that between the species of the same genus. But when we come to discuss the principle, as I call it, of divergence of character, we shall see how this may be explained, and how the lesser differences between varieties tend to increase into the greater differences between species. There is one other point which is worth notice. Varieties generally have a somewhat restricted range. This statement is indeed true, but not in the sense that they are confined to one spot. A variety may be found in the north of England, and another in the south, but it will be found that they have not got a wide range. A species may be found all over England, but it will not be found all over Europe. So it is with varieties. On the other hand, species which are very closely allied to other species, and in so far resemble varieties, have often a very restricted range. For instance, Mr. H.C. Watson has marked for me in the London Catalogue of Plants 63 plants which are ranked as species, but which he considers are so closely allied to other species as to be of doubtful value. These 63 reputed species range on an average over 6.9 of the provinces into which Mr. Watson has divided Great Britain. Now, in this same catalogue, 53 acknowledged varieties are recorded, and these range over 7.7 provinces, whereas the species to which these varieties belong range over 14.3 provinces, so that the acknowledged varieties have nearly the same restricted average range as have the closely allied forms marked for me by Mr. Watson as doubtful species, but which are almost universally ranked by British botanists as good and true species. Finally, varieties cannot be distinguished from species, except first by the discovery of intermediate linking forms, and secondly by a certain indefinite amount of difference between them. For two forms, if differing very little, are generally ranked as varieties, notwithstanding that they cannot be closely connected, but the amount of difference considered necessary to give to any two forms the rank of species is quite indefinite. In genera which have a large number of species, as compared with other genera of the same family, the species of these large genera present a number of varieties, or incipient species, greater than the average, and this holds good, not only in the same country, but as far as I have been able to ascertain in other countries also. The species of large genera are apt to be closely but unequally allied to each other, and to have restricted ranges. In all these respects, the species of large genera present a strong analogy with varieties, and we can clearly understand these analogies if species have once existed as varieties and have thus originated, whereas these analogies are utterly inexplicable if species are independent creations. We have also seen that it is the most flourishing or dominant species of the larger genera within each class which on an average yield the greatest number of varieties. And varieties, as we shall hereafter see, tend to become converted into new and distinct species. Thus it is in the most flourishing groups that the greatest number of new species have been formed, where many species of a genus have been formed. On an average many are still forming, and this holds good not only wherever a genus has a large number of species in one country, but in all countries, and as a general rule the species of each genus inhabiting any country are numerous in proportion to the number of species of the same genus inhabiting the world. This is what might have been expected, for the species of a genus are all related to each other, and are therefore adapted to nearly the same climate and station, so that we can see why it is that the flora of a small island or of a lake is generally poor in species, compared with that of a large island or a continent. So also we can see why it is that the alpine flora of a mountain range is poor in species, compared with the flora of the lowlands. The smallness of the area, and the small number of the inhabitants, will in both cases have checked the production of new species and will have favoured the immigration of species already formed in other countries. From these considerations, I think a startling result follows, namely, that as new species in the course of time are formed through natural selection, others will become rarer and rarer, and finally extinct. The forms which stand in closest competition with those undergoing modification and improvement will naturally suffer most. And we have seen in the chapter on the struggle for existence that it is the most closely allied forms, varieties of the same species, and species of the same genus or of related genera, which from having nearly the same structure, constitution and habits, generally come into the severest competition with each other. Consequently, each new variety or species during the progress of its formation will generally press hardest on its nearest kindred and tend to exterminate them. We see the same process of extermination among our domesticated productions through the selection of improved forms by man. Many curious instances could be given, showing how quickly new breeds of cattle, sheep and other animals, and new varieties of flowers, take the place of older and inferior kinds. In Yorkshire, it is historically known that the ancient black cattle were displaced by the longhorns, and that these were swept away by the shorthorns, as if by some murderous pestilence. We see in this case a striking instance of the law of extermination of the old and inferior by the new and improved forms. It is just what we should have expected on my theory, and it is what we find to be the case in nature. I have now recapitulated the chief facts and considerations which have thoroughly convinced me that species have been modified during a long course of descent. This has been effected chiefly through the natural selection of numerous successive, slight, favourable variations, aided in an important manner by the inherited effects of the use and disuse of parts, and in an unimportant manner, that is in relation to adaptive structures, whether past or present, by the direct action of external conditions, and by variations which seem to us in our ignorance to arise spontaneously. It appears that I formerly underrated the frequency and value of these latter forms of variation, as leading to permanent modifications of structure independently of natural selection, but as my conclusions have lately been much misrepresented, and it has been stated that I attribute the modification of species exclusively to natural selection, I may be permitted to remark that in the first edition of this work and subsequently, I placed in a most conspicuous position, namely at the close of the introduction, the following words: "I am convinced that natural selection has been the main but not the exclusive means of modification." This has been of no avail. Great is the power of steady misrepresentation, but the progress of science and of truth may be calmly waited for. I shall now enter on the more immediate subject of this work. We have seen in the last chapter that amongst organic beings in a state of nature there is some individual variability. Indeed, I am not aware that this has ever been disputed. It is immaterial for us whether a multitude of doubtful forms be called species or subspecies or varieties. What rank, for instance, the 200 or 300 doubtful forms of British plants are entitled to hold, if the existence of any well-marked varieties be admitted? But the mere existence of individual variability and of some few well-marked varieties, though necessary as the foundation for the work, helps us but little in understanding how species arise in nature. How have all those exquisite adaptations of one part of the organization to another part, and to the conditions of life and of one organic being to another being, been perfected? We see these beautiful co-adaptations most plainly in the woodpecker and in the mistletoe, and only a little less plainly in the humblest parasite which clings to the hairs of a quadruped or feathers of a bird, in the structure of the beetle which dives through the water, in the plumed seed which is wafted by the gentlest breeze. In short, we see beautiful adaptations everywhere and in every part of the organic world. Again, it may be asked, how is it that varieties which I have called incipient species become ultimately converted into good and distinct species, which in most cases obviously differ from each other, far more than do the varieties of the same species? How do those groups of species which constitute what are called distinct genera, and which differ from each other more than do the species of the same genus, arise? All these results, as we shall more fully see in the next chapter, follow from the struggle for life. Owing to this struggle, variations, however slight, and from whatever cause proceeding, if they be in any degree profitable to the individuals of a species, in their infinitely complex relations to other organic beings and to their physical conditions of life, will tend to the preservation of such individuals and will generally be inherited by the offspring. The offspring also will thus have a better chance of surviving, for of the many individuals of any species which are periodically born, but a small number can survive. I have called this principle, by which each slight variation, if useful, is preserved, by the term natural selection, in order to mark its relation to man's power of selection. But the expression often used by Mr. Herbert Spencer of the survival of the fittest is more accurate, and is sometimes equally convenient. We have seen that man by selection can certainly produce great results, and can adapt organic beings to his own uses, through the accumulation of slight but useful variations given to him by the hand of nature. But natural selection, as we shall hereafter see, is a power incessantly ready for action, and is as immeasurably superior to man's feeble efforts as the works of nature are to those of art. We will now discuss in a little more detail the struggle for existence. In my future work this subject will be treated, as it well deserves, at greater length. The elder Decandolle and Lyell have largely and philosophically shown that all organic beings are exposed to severe competition. In regard to plants, no one has treated this subject with more spirit and ability than W. Herbert, Dean of Manchester. Evidently the result of his great horticultural knowledge, nothing is easier than to admit in words the truth of the universal struggle for life, or more difficult, at least I have found it so, than constantly to bear this conclusion in mind. Yet unless it be thoroughly ingrained in the mind, the whole economy of nature, with every fact on distribution, rarity, abundance, extinction and variation, will be dimly seen or quite misunderstood. We behold the face of nature bright with gladness. We often see superabundance of food. We do not see, or we forget, that the birds which are idly singing round us mostly live on insects or seeds, and are thus constantly destroying life. Or we forget how many of these songsters, or of their eggs, or of their nestlings, are destroyed by birds and beasts of prey. We do not always bear in mind that though food may be now superabundant, it is not so at all seasons of each recurring year. I should premise that I use this term in a large and metaphorical sense, including dependence of one being on another, and including, which is more important, not only the life of the individual, but success in leaving progeny. Two canine animals in a time of dearth may be truly said to struggle with each other which shall get food and live. But a plant on the edge of a desert is said to struggle for life against the drought, though more properly it should be said to be dependent on the moisture. A plant which annually produces 1,000 seeds, of which only one on an average comes to maturity, may be more truly said to struggle with the plants of the same and other kinds which already clothe the ground. The mistletoe is dependent on the apple and a few other trees, but can only in a far-fetched sense be said to struggle with these trees, for if too many of these parasites grow on the same tree, it languishes and dies. But several seedling mistletoes growing close together on the same branch may more truly be said to struggle with each other. As the mistletoe is disseminated by birds, its existence depends on them, and it may metaphorically be said to struggle with other fruit-bearing plants, in tempting the birds to devour and thus disseminate its seeds. In these several senses which pass into each other, I use for convenience sake the general term of struggle for existence. A struggle for existence inevitably follows from the high rate at which all organic beings tend to increase. Every being, which during its natural lifetime produces several eggs or seeds, must suffer destruction during some period of its life, and during some season or occasional year. Otherwise, on the principle of geometrical increase, its numbers would quickly become so inordinately great that no country could support the product. Hence, as more individuals are produced than can possibly survive, there must in every case be a struggle for existence, either one individual with another of the same species, or with the individuals of distinct species, or with the physical conditions of life. It is the doctrine of Malthus applied with manifold force to the whole animal and vegetable kingdoms, for in this case there can be no artificial increase of food and no prudential restraint from marriage. Although some species may be now increasing, more or less rapidly in numbers, all cannot do so, for the world would not hold them. There is no exception to the rule that every organic being naturally increases at so high a rate that if not destroyed, the earth would soon be covered by the progeny of a single pair. Even slow-breeding man has doubled in 25 years, and at this rate, in less than 1,000 years there would literally not be standing room for his progeny. Linnaeus has calculated that if an annual plant produced only 2 seeds, and there is no plant so unproductive as this, and their seedlings next year produce 2, and so on, then in 20 years there would be 1,000,000 plants. The elephant is reckoned the slowest breeder of all known animals, and I have taken some pains to estimate its probable minimum rate of natural increase. It will be safest to assume that it begins breeding when 30 years old, and goes on breeding till 90 years old, bringing forth 6 young in the interval, and surviving till 100 years old. If this be so, after a period of from 740 to 750 years, there would be nearly 19 million elephants alive, descended from the first pair. But we have better evidence on this subject than mere theoretical calculations, namely, the numerous recorded cases of the astonishingly rapid increase of various animals in a state of nature, when circumstances have been favourable to them during 2 or 3 following seasons. Still more striking is the evidence from our domestic animals of many kinds, which have run wild in several parts of the world. If the statements of the rate of increase of slow-breeding cattle and horses in South America and latterly in Australia had not been well authenticated, they would have been incredible. So it is with plants. Cases could be given of introduced plants which have become common throughout whole islands in a period of less than 10 years. Several of the plants, such as the cardoon and a tall thistle, which are now the commonest over the wide plains of La Plata, clothing square leagues of surface almost to the exclusion of every other plant, have been introduced from Europe. To such cases as these, which I could add others, Dr. Falconer has lately communicated to me a curious instance, namely, that the watercress Nasturtium officinale has spread in New Zealand, where it was introduced only a few years ago, so as to choke up the rivers and streams. In looking at nature, it is most necessary to keep the foregoing considerations always in mind, never to forget that every single organic being may be said to be striving to the utmost to increase in numbers, that each lives by a struggle at some period of its life, that heavy destruction inevitably falls either on the young or old during each generation or at recurrent intervals. Lighten any check, mitigate the destruction ever so little, and the number of the species will almost instantaneously increase to any amount. The causes which check the natural tendency of each species to increase are most obscure. Look at the most vigorous species by as much as it swarms in numbers. By so much will it tend to increase still further. We know not exactly what the checks are even in a single instance, nor will this surprise anyone who reflects how ignorant we are on this head, even in regard to mankind, although so incomparably better known than any other animal. This subject of the checks to increase has been ably treated by several authors, and I hope in a future work to discuss it at considerable length, more especially in regard to the feral animals of South America. Here I will make only a few remarks just to recall to the reader's mind some of the chief points. Eggs or very young animals seem generally to suffer most, but this is not invariably the case. With plants there is a vast destruction of seeds, but from some observations which I have made, it appears that the seedlings suffer most from germinating in ground already thickly stocked with other plants. Seedlings also are destroyed in vast numbers by various enemies. For instance, on a piece of ground 3 feet long and 2 wide, dug and cleared, and where there could be no choking from other plants, I marked all the seedlings of our native weeds as they came up, and out of 357 no less than 295 were destroyed, chiefly by slugs and insects. If turf which has long been mown, and the case would be the same with turf closely browsed by quadrupeds, be let to grow, the more vigorous plants gradually kill the less vigorous though fully grown plants. Thus out of 20 species growing on a little plot of mown turf, 3 feet by 4, 9 species perished, from the other species being allowed to grow up freely. The amount of food for each species of course gives the extreme limit to which each can increase, but very frequently it is not the obtaining food but the serving as prey to other animals, which determines the average numbers of a species. Thus there seems to be little doubt that the stock of partridges, grouse and hares on any large estate depends chiefly on the destruction of vermin. If not one head of game were shot during the next 20 years in England, and at the same time if no vermin were destroyed, there would in all probability be less game than at present, although hundreds of thousands of game animals are now annually killed. On the other hand, in some cases, as with the elephant, none are destroyed by beasts of prey, for even the tiger in India most rarely dares to attack a young elephant protected by its dam. Climate plays an important part in determining the average numbers of a species, and periodical seasons of extreme cold or drought seem to be the most effective of all checks. I estimated, chiefly from the greatly reduced numbers of nests in the spring, that the winter of 1854-6 destroyed 4/5 of the birds in my own grounds, and this is a tremendous destruction when we remember that 10% is an extraordinarily severe mortality from epidemics with man. The action of climate seems at first sight to be quite independent of the struggle for existence, but insofar as climate chiefly acts in reducing food, it brings on the most severe struggle between the individuals, whether of the same or of distinct species, which subsist on the same kind of food. Even when climate, for instance extreme cold, acts directly, it will be the least vigorous individuals, or those which have got least food through the advancing winter, which will suffer most. When we travel from south to north or from a damp region to a dry, we invariably see some species gradually getting rarer and rarer, and finally disappearing, and the change of climate being conspicuous. We are tempted to attribute the whole effect to its direct action, but this is a false view. We forget that each species, even where it most abounds, is constantly suffering enormous destruction at some period of its life, from enemies or from competitors for the same place and food, and if these enemies or competitors be in the least degree favoured by any slight change of climate, they will increase in numbers, and as each area is already fully stocked with inhabitants, the other species must decrease. When we travel southward and see a species decreasing in numbers, we may feel sure that the cause lies quite as much in other species being favoured as in this one being hurt. So it is when we travel northward, but in a somewhat lesser degree, for the number of species of all kinds, and therefore of competitors, decreases northwards. Hence, in going northwards, or in ascending a mountain, we far oftener meet with stunted forms due to the directly injurious action of climate, than we do in proceeding southwards, or in descending a mountain. When we reach the Arctic regions or snow-capped summits or absolute deserts, the struggle for life is almost exclusively with the elements. That climate acts in main part indirectly by favouring other species. We may clearly see in the prodigious number of plants which in our gardens can perfectly well endure our climate, but which never become naturalised, for they cannot compete with our native plants nor resist destruction by our native animals. When a species, owing to highly favourable circumstances, increases inordinately in numbers in a small tract, epidemics at least, this seems generally to occur with our game animals, often ensue, and here we have a limiting check independent of the struggle for life. But even some of these so-called epidemics appear to be due to parasitic worms, which have from some cause, possibly in part through facility of diffusion amongst the crowded animals, been disproportionately favoured. And here comes in a sort of struggle between the parasite and its prey. On the other hand, in many cases, a large stock of individuals of the same species, relatively to the numbers of its enemies, is absolutely necessary for its preservation. Thus we can easily raise plenty of corn and rapeseed, etc. in our fields because the seeds are in great excess, but it is not so with all plants. I have been surprised to find that the carline thistle, Carlina vulgaris, which is very common in some parts of England, has its seeds almost all destroyed by a species of seed weevil, and this thistle has been almost exterminated by it in some places. I have seen the same thing with the common red clover, Trifolium pratense, the seeds of which are destroyed by a species of weevil. Hence it is that such plants as these are only preserved by their seeds being sown in large quantities, and thus some escaping destruction. In the case of the carline thistle, it has been observed that the seeds sown in gardens have not produced a single plant. This shows how necessary it is that a large stock of individuals of the same species should exist, in order that some may escape destruction. Many cases are on record showing how complex and unexpected are the checks and relations between organic beings, which have to struggle together in the same country. I will give only a single instance, which, though a simple one, interested me. In Staffordshire, on the estate of a relation, where I had ample means of investigation, there was a large and extremely barren heath, which had never been touched by the hand of man, but several hundred acres of exactly the same nature had been enclosed 25 years previously and planted with Scotch fir. The change in the native vegetation of the planted part of the heath was most remarkable, more than is generally seen in passing from one quite different soil to another. Not only the proportional numbers of the heath plants were wholly changed, but 12 species of plants, not counting grasses and carices, flourished in the plantations, which could not be found on the heath. The effect on the insects must have been still greater, for 6 insectivorous birds were very common in the plantations, which were not to be seen on the heath, and the heath was frequented by 2 or 3 distinct insectivorous birds. Here we see how potent has been the effect of the introduction of a single tree, nothing whatever else having been done, with the exception of the land having been enclosed so that cattle could not enter. But how important an element enclosure is, I plainly saw near Farnham in Surrey. Here there are extensive heaths with a few clumps of old Scotch firs on the distant hilltops. Within the last 10 years large spaces have been enclosed, and self-sown firs are now springing up in multitudes, so close together that all cannot live. When I ascertained that these young trees had not been sown or planted, I was so much surprised at their numbers that I went to several points of view whence I could examine hundreds of acres of the unenclosed heath, and literally not a single Scotch fir could be seen, except the old planted clumps. But on looking closely between the stems of the heath, I found a multitude of seedlings and little trees which had been perpetually browsed down by the cattle. In 1 square yard, at a point some 100 yards distant from one of the old clumps, I counted 32 little trees, and one of them, with 26 rings of growth, had during many years tried to raise its head above the stems of the heath, and had failed. No wonder that, as soon as the land was enclosed, it became thickly clothed with vigorously growing young firs. Yet the heath was so extremely barren and so extensive that no one would ever have imagined that cattle would have so closely and effectually searched it for food. Many cases are on record showing how complex and unexpected are the checks and relations between organic beings, which have to struggle together in the same country. I will give only a single instance, which, though a simple one, interested me. In Staffordshire, on the estate of a relation, where I had ample means of investigation, there was a large and extremely barren heath, which had never been touched by the hand of man, but several hundred acres of exactly the same nature had been enclosed 25 years previously and planted with Scotch fir. The change in the native vegetation of the planted part of the heath was most remarkable, more than is generally seen in passing from one quite different soil to another. Not only the proportional numbers of the heath plants were wholly changed, but 12 species of plants, not counting grasses and carices, flourished in the plantations, which could not be found on the heath. The effect on the insects must have been still greater, for 6 insectivorous birds were very common in the plantations, which were not to be seen on the heath, and the heath was frequented by 2 or 3 distinct insectivorous birds. Here we see how potent has been the effect of the introduction of a single tree, nothing whatever else having been done, with the exception of the land having been enclosed so that cattle could not enter. But how important an element enclosure is, I plainly saw near Farnham in Surrey. Here there are extensive heaths with a few clumps of old Scotch firs on the distant hilltops. Within the last 10 years large spaces have been enclosed, and self-sown firs are now springing up in multitudes, so close together that all cannot live. When I ascertained that these young trees had not been sown or planted, I was so much surprised at their numbers that I went to several points of view whence I could examine hundreds of acres of the unenclosed heath, and literally not a single Scotch fir could be seen, except the old planted clumps. But on looking closely between the stems of the heath, I found a multitude of seedlings and little trees which had been perpetually browsed down by the cattle. In 1 square yard, at a point some 100 yards distant from one of the old clumps, I counted 32 little trees, and one of them, with 26 rings of growth, had during many years tried to raise its head above the stems of the heath, and had failed. No wonder that, as soon as the land was enclosed, it became thickly clothed with vigorously growing young firs. Yet the heath was so extremely barren and so extensive that no one would ever have imagined that cattle would have so closely and effectually searched it for food. Here we see that cattle absolutely determine the existence of the Scotch fir. But in several parts of the world, insects determine the existence of cattle. Perhaps Paraguay offers the most curious instance of this, for here neither cattle nor horses nor dogs have ever run wild, though they swarm southward and northward in a feral state, and Azara and Renga have shown that this is caused by the greater number in Paraguay of a certain fly, which lays its eggs in the navels of these animals when first born. The increase of these flies, numerous as they are, must be habitually checked by some means, probably by other parasitic insects. Hence, if certain insectivorous birds were to decrease in Paraguay, the parasitic insects would probably increase, and this would lessen the number of the navel-frequenting flies. Then cattle and horses would become feral, and this would certainly greatly alter, as indeed I have observed in parts of South America, the vegetation. This again would largely affect the insects, and this, as we have just seen in Staffordshire, the insectivorous birds, and so onwards in ever-increasing circles of complexity. Not that under nature the relations will ever be as simple as this. Battle within battle must be continually recurring with varying success, and yet in the long run the forces are so nicely balanced that the face of nature remains for long periods of time uniform, though assuredly the merest trifle would give the victory to one organic being over another. Nevertheless, so profound is our ignorance and so high our presumption that we marvel when we hear of the extinction of an organic being, and as we do not see the cause, we invoke cataclysms to desolate the world, or invent laws on the duration of the forms of life. I am tempted to give one more instance showing how plants and animals, remote in the scale of nature, are bound together by a web of complex relations. I shall hereafter have occasion to show that the exotic Lobelia fulgens is never visited in my garden by insects, and consequently, from its peculiar structure, never sets a seed. Nearly all our orchidaceous plants absolutely require the visits of insects to remove their pollen masses and thus to fertilize them. I find from experiments that humble bees are almost indispensable to the fertilization of the heartsease Viola tricolor, for other bees do not visit this flower. I have also found that the visits of bees are necessary for the fertilization of some kinds of clover. For instance, 20 heads of Dutch clover, Trifolium repens, yielded 2,290 seeds, but 20 other heads protected from bees produced not one. Again, 100 heads of red clover, T. pretense, produced 2,700 seeds, but the same number of protected heads produced not a single seed. Humble bees alone visit red clover, as other bees cannot reach the nectar. It has been suggested that moths may fertilize the clovers, but I doubt whether they could do so in the case of the red clover, from their weight not being sufficient to depress the wing petals. Hence we may infer as highly probable that if the whole genus of humble bees became extinct or very rare in England, the heartsease and red clover would become very rare or wholly disappear. The number of humble bees in any district depends in a great measure upon the number of field mice, which destroy their combs and nests, and Cole Newman, who has long attended to the habits of humble bees, believes that more than 2/3 of them are thus destroyed all over England. Now the number of mice is largely dependent, as everyone knows, on the number of cats, and Cole Newman says, "Near villages and small towns I have found the nests of humble bees more numerous than elsewhere, which I attribute to the number of cats that destroy the mice." Hence it is quite credible that the presence of a feline animal in large numbers in a district might determine, through the intervention first of mice and then of bees, the frequency of certain flowers in that district. In the case of every species, many different checks acting at different periods of life, and during different seasons or years, probably come into play. Some one check or some few being generally the most potent, but all will concur in determining the average number or even the existence of the species. In some cases, it can be shown that widely different checks act on the same species in different districts. When we look at the plants and bushes clothing an entangled bank, we are tempted to attribute their proportional numbers and kinds to what we call chance. But how false a view is this? Everyone has heard that when an American forest is cut down, a very different vegetation springs up. But it has been observed that ancient Indian ruins in the southern United States, which must formerly have been cleared of trees, now display the same beautiful diversity and proportion of kinds as in the surrounding virgin forest. What a struggle must have gone on during long centuries between the several kinds of trees, each annually scattering its seeds by the thousand. What war between insect and insect between insects, snails and other animals with birds and beasts of prey, all striving to increase, all feeding on each other, or on the trees, their seeds and seedlings, or on the other plants which first clothe the ground and thus check the growth of the trees. Throw up a handful of feathers and all fall to the ground according to definite laws. But how simple is the problem where each shall fall compared to that of the action and reaction of the innumerable plants and animals which have determined in the course of centuries the proportional numbers and kinds of trees now growing on the old Indian ruins. The dependency of one organic being on another, as of a parasite on its prey, lies generally between beings remote in the scale of nature. This is likewise sometimes the case with those which may be strictly said to struggle with each other for existence, as in the case of locusts and grass-feeding quadrupeds. But the struggle will almost invariably be most severe between the individuals of the same species, for they frequent the same districts, require the same food, and are exposed to the same dangers. In the case of varieties of the same species, the struggle will generally be almost equally severe, and we sometimes see the contest soon decided. For instance, if several varieties of wheat be sown together, and the mixed seed be resown, some of the varieties which best suit the soil or climate, or are naturally the most fertile, will beat the others, and so yield more seed, and will consequently in a few years supplant the other varieties. To keep up a mixed stock of even such extremely close varieties as the variously coloured sweet peas, they must be each year harvested separately, and the seed then mixed in due proportion, otherwise the weaker kinds will steadily decrease in number and disappear. So again with the varieties of sheep, it has been asserted that certain mountain varieties will starve out other mountain varieties, so that they cannot be kept together. The same result has followed from keeping together different varieties of the medicinal leech. It may even be doubted whether the varieties of any of our domestic plants or animals have so exactly the same strength, habits and constitution that the original proportions of a mixed stock crossing being prevented could be kept up for half a dozen generations if they were allowed to struggle together in the same manner as beings in a state of nature, and if the seed or young were not annually preserved in due proportion, as the species of the same genus usually have, though by no means invariably. Much similarity in habits and constitution, and always in structure. The struggle will generally be more severe between them if they come into competition with each other than between the species of distinct genera. We see this in the recent extension over parts of the United States of one species of swallow having caused the decrease of another species. The recent increase of the missel thrush in parts of Scotland has caused the decrease of the song thrush. How frequently we hear of one species of rat taking the place of another species under the most different climates. In Russia, the small Asiatic cockroach has everywhere driven before it its great congener. In Australia, the imported hive bee is rapidly exterminating the small stingless native bee. One species of charlock has been known to supplant another species, and so in other cases, we can dimly see why the competition should be most severe between allied forms, which fill nearly the same place in the economy of nature, but probably in no one case could we precisely say why one species has been victorious over another in the great battle of life. A corollary of the highest importance may be deduced from the foregoing remarks, namely that the structure of every organic being is related in the most essential yet often hidden manner to that of all the other organic beings, with which it comes into competition for food or residence, or from which it has to escape, or on which it preys. This is obvious in the structure of the teeth and talons of the tiger, and in that of the legs and claws of the parasite which clings to the hair on the tiger's body, but in the beautifully plumed seed of the dandelion, and in the flattened and fringed legs of the water beetle, the relation seems at first confined to the elements of air and water, yet the advantage of plumed seeds no doubt stands in the closest relation to the land being already thickly clothed with other plants, so that the seeds may be widely distributed and fall on unoccupied ground. In the water beetle, the structure of its legs, so well adapted for diving, allows it to compete with other aquatic insects, to hunt for its own prey, and to escape serving as prey to other animals. The store of nutriment laid up within the seeds of many plants seems at first sight to have no relation to other plants, but from the strong growth of young plants produced from such seeds, as peas and beans, when sown in the midst of long grass, it may be suspected that the chief use of the nutriment in the seed is to favour the growth of the seedlings, while struggling with other plants growing vigorously all around. Look at a plant in the midst of its range. Why does it not double or quadruple its numbers? We know that it can perfectly well withstand a little more heat or cold, humidity or dryness, for elsewhere it ranges into slightly hotter or colder, damper or drier districts. In this case, we can clearly see that if we wish in imagination to give the plant the power of increasing in number, we should have to give it some advantage over its competitors, or over the animals which prey on it. On the confines of its geographical range, a change of constitution with respect to climate would clearly be an advantage to our plant, but we have reason to believe that only a few plants or animals range so far that they are destroyed exclusively by the rigor of the climate. Not until we reach the extreme confines of life in the Arctic regions or on the borders of an utter desert will competition cease. The land may be extremely cold or dry, yet there will be competition between some few species or between the individuals of the same species for the warmest or dampest spots. Hence, we can see that when a plant or animal is placed in a new country amongst new competitors, the conditions of its life will generally be changed in an essential manner, although the climate may be exactly the same as in its former home. If its average numbers are to increase in its new home, we should have to modify it in a different way to what we should have had to do in its native country, for we should have to give it some advantage over a different set of competitors or enemies. It is good thus to try in imagination to give to any one species an advantage over another. Probably in no single instance should we know what to do. This ought to convince us of our ignorance on the mutual relations of all organic beings, a conviction as necessary as it is difficult to acquire. All that we can do is to keep steadily in mind that each organic being is striving to increase in a geometrical ratio, that each at some period of its life, during some season of the year, during each generation or at intervals, has to struggle for life and to suffer great destruction. When we reflect on this struggle, we may console ourselves with the full belief that the war of nature is not incessant, that no fear is felt, that death is generally prompt, and that the vigorous, the healthy, and the happy survive and multiply. How will the struggle for existence, briefly discussed in the last chapter, act in regard to variation? Can the principle of selection, which we have seen is so potent in the hands of man, apply under nature? I think we shall see that it can act most efficiently. Let the endless number of slight variations and individual differences occurring in our domestic productions, and in a lesser degree in those under nature, be kept in mind, as well as the strength of the hereditary tendency. Under domestication, it may be truly said that the whole organization becomes in some degree plastic. But the variability which we almost universally meet with in our domestic productions is not directly produced by man. He can neither originate variations nor prevent their occurrence. He can only preserve and accumulate such as do occur. Unintentionally, he exposes organic beings to new and changing conditions of life, and variability ensues, but similar changes of conditions might and do occur under nature. Let it also be borne in mind how infinitely complex and close-fitting are the mutual relations of all organic beings to each other, and to their physical conditions of life, and consequently what infinitely varied diversities of structure might be of use to each being under changing conditions of life. Can it then be thought improbable, seeing that variations useful to man have undoubtedly occurred, that other variations useful in some way to each being in the great and complex battle of life should occur in the course of many successive generations? If such do occur, can we doubt, remembering that many more individuals are born than can possibly survive, that individuals having any advantage, however slight, over others would have the best chance of surviving and of procreating their kind? On the other hand, we may feel sure that any variation in the least degree injurious would be rigidly destroyed. This preservation of favorable individual differences and variations, and the destruction of those which are injurious, I have called natural selection, or the survival of the fittest. Variations neither useful nor injurious would not be affected by natural selection, and would be left either a fluctuating element, as perhaps we see in certain polymorphic species, or would ultimately become fixed owing to the nature of the organism and the nature of the conditions. Several writers have misapprehended or objected to the term natural selection. Some have even imagined that natural selection induces variability, whereas it implies only the preservation of such variations as arise and are beneficial to the being under its conditions of life. No one objects to agriculturists speaking of the potent effects of man's selection, and in this case the individual differences given by nature which man for some object selects must of necessity first occur. Others have objected that the term selection implies conscious choice in the animals which are selected, and it has even been urged that as plants have no volition, natural selection is not applicable to them. In the literal sense of the word, no doubt natural selection is a false term, but whoever objected to chemists speaking of the elective affinities of the various elements, and yet an acid cannot strictly be said to elect the base with which it in preference combines. It has been said that I speak of natural selection as an active power or deity, but who objects to an author speaking of the attraction of gravity as ruling the movements of the planets? Everyone knows what is meant and is implied by such metaphorical expressions, and they are almost necessary for brevity. So again, it is difficult to avoid personifying the word nature, but I mean by nature only the aggregate action and product of many natural laws, and by laws the sequence of events as ascertained by us. With a little familiarity, such superficial objections will be forgotten. We shall best understand the probable course of natural selection by taking the case of a country undergoing some slight physical change, for instance, of climate. The proportional numbers of its inhabitants will almost immediately undergo a change, and some species will probably become extinct. We may conclude from what we have seen of the intimate and complex manner in which the inhabitants of each country are bound together, that any change in the numerical proportions of the inhabitants independently of the change of climate itself would seriously affect the others. If the country were open on its borders, new forms would certainly immigrate, and this would likewise seriously disturb the relations of some of the former inhabitants. Let it be remembered how powerful the influence of a single introduced tree or mammal has been shown to be. But in the case of an island, or of a country partly surrounded by barriers, into which new and better adapted forms could not freely enter, we should then have places in the economy of nature which would assuredly be better filled up, if some of the original inhabitants were in some manner modified, for had the area been open to immigration, these same places would have been seized on by intruders. In such cases, slight modifications, which in any way favoured the individuals of any species, by better adapting them to their altered conditions, would tend to be preserved, and natural selection would thus have free scope for the work of improvement. We have good reason to believe that changes in the conditions of life give a tendency to increased variability, and in the foregoing cases the conditions have changed, and this would manifestly be favourable to natural selection, by affording a better chance of the occurrence of profitable variations. Unless such occur, natural selection can do nothing. Under the term of variations, it must never be forgotten that mere individual differences are included. As man can produce a great result with his domestic animals and plants by adding up in any given direction individual differences, so could natural selection, but far more easily from having incomparably longer time for action. Nor do I believe that any great physical change as of climate or any unusual degree of isolation to check immigration is necessary in order that new and unoccupied places should be left for natural selection to fill up by modifying and improving some of the varying inhabitants. For as all the inhabitants of each country are struggling together with nicely balanced forces, extremely slight modifications in the structure or habits of one species would often give it an advantage over others, and still further modifications of the same kind would often still further increase the advantage as long as the species continued to vary, and did not transgress the standard of perfection in its organization. I will now give 2 or 3 imaginary instances. Let us take the case of a wolf which preys on various animals, securing some by craft, some by strength, and some by fleetness. And let us suppose that the fleetest prey, a deer for instance, had from any change in the country increased in numbers, or that other prey had decreased in numbers, during that season of the year when the wolf was hardest pressed for food. Under such circumstances, the swiftest and slimmest wolves would have the best chance of surviving, and so be preserved or selected, provided always that they retained strength to master their prey at this or some other period of the year when they were compelled to prey on other animals. I can see no more reason to doubt that this would be the result, than that man should be able to improve the fleetness of his greyhounds by careful and methodical selection, or by that kind of unconscious selection which follows from each man trying to keep the best dogs without any thought of modifying the breed. I may add that according to Mr. Pierce, there are 2 varieties of the wolf inhabiting the Catskill Mountains in the United States, one with a light greyhound-like form, which pursues deer, and the other more bulky, with shorter legs, which more frequently attacks the shepherd's flocks. It should be observed that, in the above illustration, I speak of the slimmest individual wolves, and not of any single strongly marked variation having been preserved. In former editions of this work I sometimes spoke as if this latter alternative had frequently occurred. I saw the great importance of individual differences, and this led me fully to discuss the results of unconscious selection by man, which depends on the preservation of all the more or less valuable individuals, and on the destruction of the worst. I saw also that the preservation in a state of nature of any occasional deviation of structure, such as a monstrosity, would be a rare event, and that if at first preserved it would generally be lost by subsequent intercrossing with ordinary individuals. Nevertheless, until reading an able and valuable article in the North British Review 1867, I did not appreciate how rarely single variations, whether slight or strongly marked, could be perpetuated. The author takes the case of a pair of animals, producing during their lifetime 200 offspring, of which from various causes of destruction only 2 on an average survive to procreate their kind. This is rather an extreme estimate for most of the higher animals, but by no means so for many of the lower organisms. He then shows that if a single individual were born, which varied in some manner, giving it twice as good a chance of life as that of the other individuals, yet the chances would be strongly against its survival, supposing it to survive and to breed, and that half its young inherited the favourable variation. Still, as the reviewer goes on to show, the young would have only a slightly better chance of surviving and breeding, and this chance would go on decreasing in the succeeding generations. The justice of these remarks cannot, I think, be disputed. If, for instance, a bird of some kind could procure its food more easily by having its beak curved, and if one were born with its beak strongly curved, and which consequently flourished, nevertheless there would be a very poor chance of this one individual perpetuating its kind to the exclusion of the common form. But there can hardly be a doubt, judging by what we see taking place under domestication, that this result would follow from the preservation during many generations of a large number of individuals with more or less curved beaks, and from the destruction of a still larger number with the straightest beaks. It should not, however, be overlooked that certain rather strongly marked variations, which no one would rank as mere individual differences, frequently recur owing to a similar organization being similarly acted on, of which fact numerous instances could be given with our domestic productions. In such cases, if the varying individual did not actually transmit to its offspring its newly acquired character, it would undoubtedly transmit to them, as long as the existing conditions remained the same, a still stronger tendency to vary in the same manner. There can also be little doubt that the tendency to vary in the same manner has often been so strong that all the individuals of the same species have been similarly modified without the aid of any form of selection, or only a third, fifth, or 10th part of the individuals may have been thus affected, of which fact several instances could be given. Thus Grubbo estimates that about 1/5 of the guillemots in the Faroe Islands consist of a variety so well marked that it was formerly ranked as a distinct species under the name of Uria lacrymans. In cases of this kind, if the variation were of a beneficial nature, the original form would soon be supplanted by the modified form through the survival of the fittest. To the effects of intercrossing and eliminating variations of all kinds, I shall have to recur, but it may be here remarked that most animals and plants keep to their proper homes and do not needlessly wander about. We see this even with migratory birds, which almost always return to the same spot. Consequently, each newly formed variety would generally be at first local, as seems to be the common rule with varieties in a state of nature, so that similarly modified individuals would soon exist in a small body together, and would often breed together. If the new variety were successful in its battle for life, it would slowly spread from a central district, competing with and conquering the unchanged individuals on the margins of an ever-increasing circle. It may be worthwhile to give another and more complex illustration of the action of natural selection. Certain plants excrete sweet juice, apparently for the sake of eliminating something injurious from the sap. This is effected, for instance, by glands at the base of the stipules in some Leguminosae, and at the backs of the leaves of the common laurel. This juice, though small in quantity, is greedily sought by insects, but their visits do not in any way benefit the plant. Now, let us suppose that the juice or nectar was excreted from the inside of the flowers of a certain number of plants of any species. Insects in seeking the nectar would get dusted with pollen and would often transport it from one flower to another. The flowers of two distinct individuals of the same species would thus be crossed, and the act of crossing, as can be fully proved, gives rise to vigorous seedlings which consequently would have the best chance of flourishing and surviving. The plants which produced flowers with the largest glands or nectaries excreting most nectar would oftenest be visited by insects and would oftenest be crossed, and so in the long run would gain the upper hand and form a local variety. The flowers also which had their stamens and pistils placed in relation to the size and habits of the particular insect which visited them, so as to favour in any degree the transportal of the pollen, would likewise be favoured. We might have taken the case of insects visiting flowers for the sake of collecting pollen instead of nectar, and as pollen is formed for the sole purpose of fertilization, its destruction appears to be a simple loss to the plant. Yet if a little pollen were carried, first occasionally and then habitually, by the pollen-devouring insects from flower to flower, and a cross thus effected, although 9/10 of the pollen were destroyed, it might still be a great gain to the plant to be thus robbed, and the individuals which produced more and more pollen and had larger anthers would be selected. When our plant, by the above process long continued, had been rendered highly attractive to insects, they would unintentionally on their part regularly carry pollen from flower to flower, and that they do this effectually I could easily show by many striking facts. I will give only one, as likewise illustrating one step in the separation of the sexes of plants. Some holly trees bear only male flowers, which have 4 stamens producing a rather small quantity of pollen and a rudimentary pistil. Other holly trees bear only female flowers. These have a full-sized pistil and 4 stamens with shriveled anthers, in which not a grain of pollen can be detected. Having found a female tree exactly 60 yards from a male tree, I put the stigmas of 20 flowers taken from different branches under the microscope, and on all without exception there were a few pollen grains, and on some a good many. As the wind had set for several days from the female to the male tree, the pollen could not thus have been carried. The weather had been cold and boisterous, and therefore not favourable to bees. Nevertheless, every female flower which I examined had been effectually fertilized by the bees, which had flown from tree to tree in search of nectar. But to return to our imaginary case, as soon as the plant had been rendered so highly attractive to insects that pollen was regularly carried from flower to flower, another process might commence. No naturalist doubts the advantage of what has been called the physiological division of labour. Hence, we may believe that it would be advantageous to a plant to produce stamens alone in one flower, or on one whole plant, and pistils alone in another flower, or on another plant. In plants under culture and placed under new conditions of life, sometimes the male organs and sometimes the female organs become more or less impotent. Now, if we suppose this to occur in ever so slight a degree under nature, then as pollen is already carried regularly from flower to flower, and as a more complete separation of the sexes of our plant would be advantageous on the principle of the division of labour, individuals with this tendency more and more developed would be continually favoured or selected, until at last a complete separation of the sexes might be effected. It would take up too much space to show the various steps through dimorphism and other means, by which the separation of the sexes in plants of various kinds is apparently now in progress, but I may add that some of the species of holly in North America are, according to Asa Gray, in an exactly intermediate condition, or as he expresses it, are more or less dioeciously polygamous. Let us now turn to the case of animals. Our domestic animals are sometimes varied by receiving characters which belong to other animals of the same family. We have evidence that this sometimes occurs under nature. The case mentioned by Mr. Blyth is of a male Himalayan rabbit which had its ears so much elongated that they hung down on each side of the head. The ears were so long that they actually measured 9 inches, though the animal itself was not large. We know that the wild rabbit has ears only about 3 inches long. This animal, living in a warm climate, had acquired ears resembling in their drooping character those of the domestic lop-eared rabbit, which is a native of a much colder country. In the case of plants, the transportal of the pollen from one flower to another is generally effected by insects or by the wind. But with animals we have an agent which is much more efficient, namely the will of the animal itself. We can see how this would act in the case of the wolf. If a variety of this animal were to arise with a longer and more slender body, and with greater fleetness, it would have a better chance of catching its prey, and so of surviving. If it were to prey on a different kind of animal, or on the same kind in a different manner, it would have a still better chance of surviving. As illustrations of the action of natural selection, I have hitherto only taken cases of organisms which have been modified in some one particular character, but it is by no means necessary that the modification should be confined to one character. We see this in our domestic productions. Man has succeeded in modifying his horses, cattle, sheep and dogs in many different ways and for many different purposes. We see this also in the different breeds of the pigeon. So it would be with organisms in a state of nature. Natural selection would be ever at work, preserving the most favorable variations in every part of the organization. Every part would be thus rendered more and more perfect in relation to the conditions of life. We can see how this would lead to that perfection of structure and co-adaptation which most justly excites our admiration. For instance, in the woodpecker, with its feet, tail, beak and tongue, so admirably adapted to catch insects under the bark of trees. In the case of the mistletoe, which draws its nourishment from certain trees, which has seeds that must be transported by certain birds, and which has flowers with separate sexes, absolutely requiring the agency of certain insects to bring pollen from one flower to the other, it is equally preposterous to account for the structure of this parasite, with its relations to several distinct organic beings, by the effects of external conditions or of habit, or of the volition of the plant itself. It is therefore of the highest importance to gain a clear insight into the means of modification and co-adaptation. At the commencement of my observations it seemed to me probable that a careful study of domesticated animals and of cultivated plants would offer the best chance of making out this obscure problem. Nor have I been disappointed. In this and in all other perplexing cases, I have invariably found that our knowledge, imperfect though it be, of variation under domestication, afforded the best and safest clue. I may venture to express my conviction of the high value of such studies, although they have been very commonly neglected by naturalists. From these considerations I shall devote the first chapter of this abstract to variation under domestication. We shall thus see that a large amount of hereditary modification is at least possible, and what is equally or more important, we shall see how great is the power of man in accumulating by his selection successive slight variations. I will then pass on to the variability of species in a state of nature, but I shall unfortunately be compelled to treat this subject far too briefly, as it can be treated properly only by giving long catalogues of facts. We shall however be enabled to discuss what circumstances are most favourable to variation. In the next chapter, the struggle for existence amongst all organic beings throughout the world, which inevitably follows from their high geometrical ratio of increase, will be treated of. This is the doctrine of Malthus, applied to the whole animal and vegetable kingdoms. As many more individuals of each species are born than can possibly survive, and as consequently there is a frequently recurring struggle for existence, it follows that any being, if it vary however slightly in any manner profitable to itself, under the complex and sometimes varying conditions of life, will have a better chance of surviving and thus be naturally selected. From the strong principle of inheritance, any selected variety will tend to propagate its new and modified form. This fundamental subject of natural selection will be treated at some length in the fourth chapter, and we shall then see how natural selection almost inevitably causes much extinction of the less improved forms of life, and induces what I have called divergence of character. In the next chapter I shall discuss the complex and little-known laws of variation and of co-adaptation. In the 4 succeeding chapters the most apparent and gravest difficulties on the theory will be given. Namely, first, the difficulties of transitions, or in understanding how a simple being or a simple organ can be changed and perfected into a highly developed being or elaborately constructed organ. Secondly, the subject of instinct or the mental powers of animals. Thirdly, hybridism, or the infertility of species and the fertility of varieties when crossed. And fourthly, the imperfection of the geological record. In the next chapter I shall consider the geological succession of organic beings throughout time, in the 12th and 13th their geographical distribution throughout space, in the 14th their classification or mutual affinities, both when mature and in an embryonic condition. In the last chapter, I shall give a brief recapitulation of the whole work and a few concluding remarks. A fair result can be obtained only by fully stating and balancing the facts and arguments on both sides of each question, and this cannot possibly be here done. I will here allude to a part of the subject which I have called sexual selection. This form of selection depends not on a struggle for existence in relation to other organic beings or to external conditions, but on a struggle between the individuals of one sex, generally the males, for the possession of the other sex. The result is not death to the unsuccessful competitor, but few or no offspring. Sexual selection is therefore less rigorous than natural selection. Generally, the most vigorous males, those which are best fitted for their places in nature, will leave most progeny, but in many cases victory depends not so much on general vigor as on having special weapons confined to the male sex. A hornless stag or spurless cock would have a poor chance of leaving numerous offspring. Sexual selection, by always allowing the victor to breed, might surely give indomitable courage, length of spur, and strength to the wing to strike in the spurred leg, in nearly the same manner as does the brutal cockfighter by the careful selection of his best cocks. How low in the scale of nature this law of battle descends, I know not. Male aguilators have been described as fighting, bellowing, and whirling round like Indians in a war dance for the possession of the females. Male salmons have been observed fighting all day long. Male stag beetles sometimes bear wounds from the huge mandibles of other males. The males of certain hymenopterous insects have been frequently seen by that inimitable observer, M. Fable, fighting for a particular female who sits by, an apparently unconcerned beholder of the struggle, and then retires with the conqueror. The war is perhaps severest between the males of polygamous animals, and these seem oftenest provided with special weapons. The males of carnivorous animals are already well armed, though to them and to others, special means of defense may be given through means of sexual selection, as the mane of the lion and the hooked jaw to the male salmon, for the shield may be as important for victory as the sword or spear. I will here allude to a part of the subject which I have called sexual selection. This form of selection depends not on a struggle for existence in relation to other organic beings or to external conditions, but on a struggle between the individuals of one sex, generally the males, for the possession of the other sex. The result is not death to the unsuccessful competitor, but few or no offspring. Sexual selection is therefore less rigorous than natural selection. Generally, the most vigorous males, those which are best fitted for their places in nature, will leave most progeny, but in many cases victory depends not so much on general vigor as on having special weapons confined to the male sex. A hornless stag or spurless cock would have a poor chance of leaving numerous offspring. Sexual selection, by always allowing the victor to breed, might surely give indomitable courage, length of spur, and strength to the wing to strike in the spurred leg, in nearly the same manner as does the brutal cockfighter by the careful selection of his best cocks. How low in the scale of nature this law of battle descends, I know not. Male alligators have been described as fighting, bellowing, and whirling round like Indians in a war dance for the possession of the females. Male salmons have been observed fighting all day long. Male stag beetles sometimes bear wounds from the huge mandibles of other males. The males of certain hymenopterous insects have been frequently seen by that inimitable observer, Fabry, fighting for a particular female who sits by, an apparently unconcerned beholder of the struggle, and then retires with the conqueror. The war is perhaps severest between the males of polygamous animals, and these seem oftenest provided with special weapons. The males of carnivorous animals are already well armed, though to them and to others special means of defense may be given through means of sexual selection, as the mane of the lion and the hooked jaw to the male salmon, for the shield may be as important for victory as the sword or spear. Amongst birds, the contest is often of a more peaceful character. All those who have attended to the subject believe that there is the severest rivalry between the males of many species to attract by singing the females. The rock thrush of Guyana, birds of paradise, and some others congregate, and successive males display with the most elaborate care, and show off in the best manner their gorgeous plumage. They likewise perform strange antics before the females, which, standing by as spectators, at last choose the most attractive partner. Those who have closely attended to birds in confinement well know that they often take individual preferences and dislikes. Thus, Sir R. Heron has described how a pied peacock was eminently attractive to all his hen birds. I cannot here enter on the necessary details, but if man can in a short time give beauty and an elegant carriage to his bantams, according to his standard of beauty, I can see no good reason to doubt that female birds, by selecting during thousands of generations the most melodious or beautiful males, according to their standard of beauty, might produce a marked effect. Some well-known laws with respect to the plumage of male and female birds in comparison with the plumage of the young can partly be explained through the action of sexual selection on variations occurring at different ages, and transmitted to the males alone or to both sexes at corresponding ages, but I have not space here to enter on this subject. Thus it is, as I believe, that when the males and females of any animal have the same general habits of life, but differ in structure, colour or ornament, such differences have been mainly caused by sexual selection, that is, by individual males having had, in successive generations, some slight advantage over other males in their weapons, means of defence, or charms, which they have transmitted to their male offspring alone. Yet I would not wish to attribute all sexual differences to this agency, for we see in our domestic animals peculiarities arising and becoming attached to the male sex, which are apparently of no direct service to this sex. A great deal of new and important information on the sexual differences of animals is given in Mr. Darwin's recent work on Descent of Man and Selection in relation to sex. Let us now see how natural selection will apply to the case of insects which are neuters, and which are consequently sterile, so that they cannot propagate their kind. The subject will be treated at greater length in the chapter on instinct, but I will here give a brief abstract of my views. In the case of social insects, we have the still more remarkable case of the workers or sterile females not only being different from the fertile females or queens, but also from the males or drones, and with ants the workers sometimes consist of 2 or 3 distinct castes which differ from each other, and from both the males and fertile females, in a most wonderful manner, so that we have here the case of a species with 3 or 4 distinct forms of individuals, all of which are sterile, and which differ from each other and from their parents in a very marked manner. I have not space here to enter on details, but I will give one instance of the differences between the workers and the fertile females. In the case of the driver ant of West Africa, the workers are of 2 sizes. The larger ones have very large heads with enormous jaws and are said to act as soldiers. The fertile females, on the other hand, have small heads with small jaws. Now, how could natural selection have acted so as to produce these sterile workers with their different forms? It is plain that the workers cannot propagate their kind, so that it is impossible that any modification of structure could have been transmitted by them to their offspring. It may be said that as the workers are produced from the eggs of the fertile females, the latter might be selected so as to produce workers of a particular form, but this would not account for the fact that the workers of the same species are sometimes of 2 or 3 distinct forms. I believe that the explanation of the whole case is as follows. The sterile workers of an insect community are in the same position with the barren flowers of a plant, which are sometimes produced on the same stock with the fertile flowers. We know that the varieties of our cultivated plants sometimes produce double flowers, which are barren. Now, if we suppose that the variations which give rise to these double flowers were useful to the plant in attracting insects so as to ensure the fertilization of the fertile flowers, then natural selection might act on the fertile plants and preserve those which produce the greatest number of barren flowers. So it is with the social insects. The workers are the barren females, and the fertile females or queens are the mothers of the whole community. The workers do not reproduce their kind, but they are of the highest importance to the community, as they perform all the labour of the hive. They are the nurses of the young, the builders of the cells, the collectors of the food, and the defenders of the community. Now, if we suppose that some of the workers in a community varied in a manner which was useful to the community, then the fertile females which produced these workers would have a better chance of leaving a numerous progeny, and thus the useful variation would be preserved and accumulated. I have not space here to enter on details, but I will give one instance of the differences between the workers and the fertile females. In the case of the driver ant of West Africa, the workers are of 2 sizes. The larger ones have very large heads with enormous jaws and are said to act as soldiers. The fertile females, on the other hand, have small heads with small jaws. Now, how could natural selection have acted so as to produce these sterile workers with their different forms? It is plain that the workers cannot propagate their kind, so that it is impossible that any modification of structure could have been transmitted by them to their offspring. It may be said that as the workers are produced from the eggs of the fertile females, the latter might be selected so as to produce workers of a particular form, but this would not account for the fact that the workers of the same species are sometimes of 2 or 3 distinct forms. I believe that the explanation of the whole case is as follows. The sterile workers of an insect community are in the same position with the barren flowers of a plant, which are sometimes produced on the same stock with the fertile flowers. We know that the varieties of our cultivated plants sometimes produce double flowers, which are barren. Now, if we suppose that the variations which give rise to these double flowers were useful to the plant in attracting insects so as to ensure the fertilization of the fertile flowers, then natural selection might act on the fertile plants and preserve those which produce the greatest number of barren flowers. So it is with the social insects. The workers are the barren females, and the fertile females or queens are the mothers of the whole community. The workers do not reproduce their kind, but they are of the highest importance to the community, as they perform all the labor of the hive. They are the nurses of the young, the builders of the cells, the collectors of the food, and the defenders of the community. Now, if we suppose that some of the workers in a community varied in a manner which was useful to the community, then the fertile females which produce these workers would have a better chance of leaving a numerous progeny, and thus the useful variation would be preserved and accumulated. But it will be said, how can this be? How can natural selection act on the fertile females so as to produce workers of a particular form? This seems at first a great difficulty, but it is not so great as it appears. We know that the varieties of our cultivated plants sometimes produce different kinds of fruit on the same tree. We know that the varieties of our domestic animals sometimes produce different kinds of offspring in the same litter. Now, if we suppose that the fertile females of a community sometimes produced workers which varied in a manner useful to the community, then the community which contained these workers would have a better chance of surviving in the struggle for existence. The fertile females of this community would have a better chance of leaving a numerous progeny, and thus the useful variation would be preserved and accumulated. The case is precisely parallel to that of the double flowers of our cultivated plants. The fertile plants which produce the greatest number of double flowers are selected, and thus the tendency to produce double flowers is increased. So it is with the social insects. The fertile females which produce the greatest number of useful workers are selected, and thus the tendency to produce useful workers is increased. We can thus understand how it is that the workers of the same species are sometimes of 2 or 3 distinct forms. For if it were useful to a community to have workers of different kinds, for instance, some to act as soldiers and others as laborers, then the fertile females which produce these different kinds of workers would have a better chance of leaving a numerous progeny, and thus the tendency to produce different kinds of workers would be increased. We have thus seen how the principle of natural selection can be applied to the case of sterile insects. I have not space here to enter on details, but I may add that the case of sterile insects is not so anomalous as it at first appears. We have other instances of sterile individuals in nature, which are useful to the community to which they belong. For instance, the barren flowers of some plants are useful in attracting insects to the fertile flowers. The neuter insects are in the same position with these barren flowers. They are useful to the community, but they do not reproduce their kind. I will now briefly recapitulate the argument. All organic beings are exposed to a severe struggle for existence. All organic beings tend to vary, however slightly, in all their parts. All variations which are in any degree profitable to the individual, in its infinitely complex relations to other organic beings, and to its physical conditions of life, will tend to the preservation of that individual, and will be inherited by its offspring. The offspring also will thus have a better chance of surviving. This is the principle of natural selection, or the survival of the fittest. It is this principle which, as I believe, has been the main but not the exclusive means of the modification of species. On the extinction of species, the subject of the extinction of species is one of the most obscure in the whole range of natural history. We know that many species have become extinct, but we do not know the causes of their extinction. It is easy to say that the extinction of a species is due to a change in the conditions of life, but this is to restate the fact. In other words, it is easy to say that the extinction of a species is due to the agency of man, but this can only apply to a few cases. It is easy to say that the extinction of a species is due to a cataclysm, but this is to invoke an imaginary cause. I believe that the extinction of a species is due to the same causes which lead to the production of new species, namely, the struggle for existence and natural selection. We have seen that the struggle for existence is most severe between the individuals of the same species and between the species of the same genus. We have seen that the species which are most numerous in individuals have the best chance of leaving a numerous progeny. Now let us suppose that a species is represented by a few individuals in a small area. These individuals will have to struggle with each other and with the individuals of other species for a scanty supply of food. They will be exposed to the attacks of enemies and to the effects of a changing climate. If the conditions of life become in any degree unfavorable, the species will be in danger of extinction. But it will be said, how can this be? How can the struggle for existence lead to the extinction of a species? We have seen that the struggle for existence leads to the preservation of the most favored individuals and races. How then can it lead to the extinction of a species? I believe that the explanation is as follows. The struggle for existence is a struggle for life and death. The individuals which are best adapted to their conditions of life will survive and multiply. The individuals which are least adapted will perish. Now, let us suppose that a species is represented by a few individuals in a small area. These individuals will be exposed to a severe struggle for existence. If the conditions of life become in any degree unfavorable, the species will be in danger of extinction. But it may be said that, as the conditions of life become unfavorable, the species will become modified so as to be better adapted to the new conditions. The modification of a species is a slow process, and it can only be effected through the preservation of favorable variations. If the conditions of life change too rapidly, the species will not have time to become modified and will perish. Moreover, the modification of a species is not always possible. There may be no favorable variations to select from, or the variations may not be of the right kind. In such cases, the species will perish. We can thus understand how it is that some species have become extinct, while others have survived. The species which have become extinct are those which have been exposed to a severe struggle for existence, and which have not been able to adapt themselves to the changing conditions of life. The species which have survived are those which have been more fortunate in the struggle for existence, and which have been able to adapt themselves to the changing conditions of life. We can also understand how it is that the extinction of a species is generally a slow process. For a species is not exterminated by a single blow. It is exterminated by a long series of unfavorable events. The individuals become rarer and rarer. The area which they inhabit becomes smaller and smaller, and at last the species disappears. The subject of the extinction of species will be treated at greater length in the chapter on the geological record. I will here only add that the extinction of a species is not a proof of any inferiority in the organization of that species. It is only a proof that the species has been unfortunate in the struggle for existence. On the geological succession of organic beings, I will now pass to the consideration of the geological succession of organic beings. This subject will be treated at greater length in my future work. Here I will only give a brief abstract of my views. The geological record is, as everyone knows, extremely imperfect. The crust of the earth is a vast museum, but the natural collections have been made only at intervals of time immensely remote. The collections are very imperfectly preserved, and they have been made in a very desultory manner. Nevertheless, the geological record, imperfect as it is, tells a clear and consistent story. It tells us that the globe has been inhabited by a succession of organic beings, which have gradually become more and more highly organized. It tells us that the species of the past have not been the same as the species of the present. It tells us that the species of the past have been related to the species of the present in the same manner as the species of one country are related to the species of another country. These facts are of the highest importance. They are utterly inexplicable on the theory of the independent creation of each species. They are perfectly intelligible on the theory of the descent of all the species of the same class from a common progenitor, with subsequent modification. Let us take the case of the mammalia. The mammalia are divided into a number of orders, such as the quadrumana, the carnivora, the rodentia, the ungulata, etc. Now, the geological record tells us that the mammalia made their first appearance on the globe at a comparatively recent period. It tells us that the first mammalia were of a low grade of organization. It tells us that the mammalia have gradually become more and more highly organized until they have culminated in man. These facts are perfectly intelligible on the theory of the descent of all the mammalia from a common progenitor, with subsequent modification, but they are utterly inexplicable on the theory of the independent creation of each species. Let us take another case. The island of Madagascar is inhabited by a number of species of lemurs, which are not found in any other part of the world. The island of Madagascar is also inhabited by a number of species of insectivorous animals, which are not found in any other part of the world. Now, the geological record tells us that the lemurs and the insectivorous animals made their first appearance on the globe at a comparatively recent period. It tells us that the lemurs and the insectivorous animals of Madagascar are related to the lemurs and the insectivorous animals of Africa, in the same manner as the species of one country are related to the species of another country. These facts are perfectly intelligible on the theory of the descent of the lemurs and the insectivorous animals of Madagascar from a common progenitor, with subsequent modification, but they are utterly inexplicable on the theory of the independent creation of each species. I will give only one more instance. The trilobites are a group of extinct crustacea, which are found in the oldest fossiliferous rocks. The trilobites are divided into a number of genera and species. Now, the geological record tells us that the trilobites made their first appearance on the globe at a very remote period. It tells us that the trilobites gradually became more and more numerous and diversified until they reached their maximum of development. It tells us that the trilobites then began to decline and that they finally became extinct. These facts are perfectly intelligible on the theory of the descent of all the trilobites from a common progenitor, with subsequent modification, but they are utterly inexplicable on the theory of the independent creation of each species. I have not space here to enter on details, but I may add that the geological record is full of similar facts. The geological record tells us that the globe has been inhabited by a succession of organic beings, which have gradually become more and more highly organized. It tells us that the species of the past have not been the same as the species of the present. It tells us that the species of the past have been related to the species of the present in the same manner as the species of one country are related to the species of another country. These facts are of the highest importance. They are utterly inexplicable on the theory of the independent creation of each species. They are perfectly intelligible on the theory of the descent of all the species of the same class from a common progenitor, with subsequent modification on the geographical distribution of organic beings. I will now pass to the consideration of the geographical distribution of organic beings. This subject will be treated at greater length in my future work. Here I will only give a brief abstract of my views. The facts of the geographical distribution of organic beings are of the highest importance. They are utterly inexplicable on the theory of the independent creation of each species. They are perfectly intelligible on the theory of the descent of all the species of the same class from a common progenitor, with subsequent modification. Let us take the case of the mammalia. The mammalia are divided into a number of orders, such as the quadrumana, the carnivora, the rodentia, the ungulata, etc. Now, the geographical distribution of the mammalia is very remarkable. The mammalia of the Old World are very different from the mammalia of the New World. The mammalia of Australia are very different from the mammalia of the rest of the world. These facts are perfectly intelligible on the theory of the descent of all the mammalia from a common progenitor, with subsequent modification, but they are utterly inexplicable on the theory of the independent creation of each species. Let us take another case. The island of Madagascar is inhabited by a number of species of lemurs, which are not found in any other part of the world. The island of Madagascar is also inhabited by a number of species of insectivorous animals, which are not found in any other part of the world. Now, the geographical distribution of the lemurs and the insectivorous animals of Madagascar is very remarkable. The lemurs and the insectivorous animals of Madagascar are related to the lemurs and the insectivorous animals of Africa in the same manner as the species of one country are related to the species of another country. These facts are perfectly intelligible on the theory of the descent of the lemurs and the insectivorous animals of Madagascar from a common progenitor with subsequent modification, but they are utterly inexplicable on the theory of the independent creation of each species. I will give only one more instance. The trilobites are a group of extinct crustacea, which are found in the oldest fossiliferous rocks. The trilobites are divided into a number of genera and species. Now, the geographical distribution of the trilobites is very remarkable. The trilobites are found in all parts of the world, but the species of one country are different from the species of another country. These facts are perfectly intelligible on the theory of the descent of all the trilobites from a common progenitor, with subsequent modification, but they are utterly inexplicable on the theory of the independent creation of each species. I have not space here to enter on details, but I may add that the geographical distribution of organic beings is full of similar facts. The geographical distribution of organic beings tells us that the globe has been inhabited by a succession of organic beings, which have gradually become more and more highly organized. It tells us that the species of the past have not been the same as the species of the present. It tells us that the species of the past have been related to the species of the present, in the same manner as the species of one country are related to the species of another country. These facts are of the highest importance. They are utterly inexplicable on the theory of the independent creation of each species. They are perfectly intelligible on the theory of the descent of all the species of the same class from a common progenitor, with subsequent modification, on the mutual affinities of organic beings, on their embryological relations, and on their rudimentary organs. I will now pass to the consideration of the mutual affinities of organic beings, of their embryological relations, and of their rudimentary organs. These subjects will be treated at greater length in my future work. Here I will only give a brief abstract of my views. The facts of the mutual affinities of organic beings are of the highest importance. They are utterly inexplicable on the theory of the independent creation of each species. They are perfectly intelligible on the theory of the descent of all the species of the same class from a common progenitor, with subsequent modification. Let us take the case of the mammalia. The mammalia are divided into a number of orders, such as the Quadrumana, the Carnivora, the Rodentia, the Ungulata, etc. Now, the mutual affinities of the mammalia are very remarkable. The mammalia of the Old World are very different from the mammalia of the New World. The mammalia of Australia are very different from the mammalia of the rest of the world. These facts are perfectly intelligible on the theory of the descent of all the mammalia from a common progenitor, with subsequent modification, but they are utterly inexplicable on the theory of the independent creation of each species. Let us take another case. The island of Madagascar is inhabited by a number of species of lemurs, which are not found in any other part of the world. The island of Madagascar is also inhabited by a number of species of insectivorous animals, which are not found in any other part of the world. Now, the mutual affinities of the lemurs and the insectivorous animals of Madagascar are very remarkable. The lemurs and the insectivorous animals of Madagascar are related to the lemurs and the insectivorous animals of Africa, in the same manner as the species of one country are related to the species of another country. These facts are perfectly intelligible on the theory of the descent of the lemurs and the insectivorous animals of Madagascar from a common progenitor, with subsequent modification, but they are utterly inexplicable on the theory of the independent creation of each species. I will give only one more instance. The trilobites are a group of extinct crustacea which are found in the oldest fossiliferous rocks. The trilobites are divided into a number of genera and species. Now, the mutual affinities of the trilobites are very remarkable. The trilobites are found in all parts of the world, but the species of one country are different from the species of another country. These facts are perfectly intelligible on the theory of the descent of all the trilobites from a common progenitor, with subsequent modification, but they are utterly inexplicable on the theory of the independent creation of each species. I have not space here to enter on details, but I may add that the mutual affinities of organic beings are full of similar facts. The mutual affinities of organic beings tell us that the globe has been inhabited by a succession of organic beings, which have gradually become more and more highly organized. It tells us that the species of the past have not been the same as the species of the present. It tells us that the species of the past have been related to the species of the present, in the same manner as the species of one country are related to the species of another country. These facts are of the highest importance. They are utterly inexplicable on the theory of the independent creation of each species. They are perfectly intelligible on the theory of the descent of all the species of the same class from a common progenitor, with subsequent modification. From the most remote period in the history of the world, organic beings have been found to resemble each other in descending degrees, so that they can be classed in groups under groups. This classification is not arbitrary like the grouping of the stars in constellations. The existence of groups would have been a mere mockery if all the species of the same genus or all the genera of the same family had been created independently. The natural system is a genealogical arrangement, with the acquired grades of difference marked by the terms varieties, species, genera, families, etc. And we have to discover the lines of descent by the most permanent characters, whatever they may be, and of however slight vital importance. The affinities of all the beings of the same class have sometimes been represented by a great tree. I believe this simile largely speaks the truth. The green and budding twigs may represent existing species, and those produced during former years may represent the long succession of extinct species. At each period of growth, all the growing twigs have tried to branch out on all sides, and to overtop and kill the surrounding twigs and branches, in the same manner as species and groups of species have at all times overmastered other species in the great battle for life. The limbs divided into great branches, and these into lesser and lesser branches, were themselves once, when the tree was young, budding twigs, and this connection of the former and present buds by ramifying branches may well represent the classification of all extinct and living species in groups subordinate to groups. Of the many twigs which flourished when the tree was a mere bush, only 2 or 3, now grown into great branches, yet survive and bear the other branches. So with the species which lived during long past geological periods, very few have left living and modified descendants. From the first growth of the tree, many a limb and branch has decayed and dropped off, and these fallen branches of various sizes may represent those whole orders, families and genera which have now no living representatives, and which are known to us only in a fossil state. As we here and there see a thin straggling branch springing from a fork low down in a tree, and which by some chance has been favoured and is still alive on its summit, so we occasionally see an animal like the Ornithorhynchus or Lepidosiren, which in some small degree connects by its affinities 2 large branches of life, and which has apparently been saved from fatal competition by having inhabited a protected station. As buds give rise by growth to fresh buds, and these, if vigorous, branch out and overtop on all sides many a feebler branch, so by generation I believe it has been with the great tree of life, which fills with its dead and broken branches the crust of the earth, and covers the surface with its ever-branching and beautiful ramifications. I have not space here to discuss the various definitions which have been given of the term species. No one definition has as yet satisfied all naturalists. Yet every naturalist knows vaguely what he means when he speaks of a species. Generally the term includes the unknown element of a distinct act of creation. The term variety is almost equally difficult to define, but here community of descent is almost universally implied, though it can rarely be proved. We have also what are called monstrosities, but they graduate into varieties by imperceptible steps. We have seen that the species of the same genus are not equally distinct from each other, that some are very closely allied, and that others are much more distinct. We have seen that the species of large genera are more closely allied to each other than are the species of small genera. We have seen that the species of a genus can be grouped into subgenera, and the species of a subgenus into lesser groups. All these facts are explained on the theory of descent with modification. The structure of the embryo is often of more importance in classification than the structure of the adult, for the embryo is the animal in its less modified state, and it is the less modified state which we want to get at in order to discover the real affinities of the animal. The embryo of a mammal, a bird, a reptile, and a fish are all very much alike, but the adult forms are very different. This shows that all these animals have descended from a common progenitor, and that the differences between them have been produced by subsequent modification. The homological relations of the parts of the same animal are of the highest importance in classification. The wing of a bat, the flipper of a porpoise, the leg of a horse, and the arm of a man are all constructed on the same general plan. They all consist of the same bones, arranged in the same order. This shows that all these animals have descended from a common progenitor, and that the differences between them have been produced by subsequent modification. Rudimentary organs are of the highest importance in classification. The wings of the ostrich are rudimentary. They are of no use for flight. The teeth of the whale are rudimentary. They never cut through the gums. The tail of the man is rudimentary. It is a mere vestige. All these facts are explained on the theory of descent, with modification. They show that the ostrich has descended from a bird which had well-developed wings, that the whale has descended from an animal which had well-developed teeth, and that man has descended from an animal which had a well-developed tail. It is a truly wonderful fact, the wonder of which we are apt to overlook from familiarity, that all animals and all plants throughout all time and space should be related to each other in groups, subordinate to groups, in the manner which we everywhere behold, namely, varieties of the same species most closely related, species of the same genus, less closely and unequally related, forming sections and subgenera, species of distinct genera much less closely related, and genera related in different degrees, forming subfamilies, families, orders, subclasses, and classes. The several subordinate groups in any class cannot be ranked in a single file, but seem clustered round points, and these round other points, and so on in almost endless cycles. If species had been created independently, no explanation would have been possible of this kind of classification, but it is explained through inheritance and the complex action of natural selection, entailing extinction and divergence of character, as we have seen illustrated in the diagram. The affinities of the beings of the same class in their adult and embryonic states are evidently of this nature. So are the relations between the domestic races and the aboriginal species. So are the relations between the species of a genus and between the genera of a family. All these relations are explained on the theory of descent with modification. The great feature in the classification of organic beings is that they are arranged in groups under groups, and these groups are not artificially arranged but are founded on natural affinities. This is what we should expect on the theory of descent with a modification. For the species of a genus are the modified descendants of a common progenitor, the genera of a family are the modified descendants of a more remote common progenitor, and so on. The embryological relations of organic beings are of the highest importance. The embryos of the most distinct species of the same class are often wonderfully like each other. The embryos of a mammal, a bird, a reptile, and a fish are at first hardly distinguishable from each other. This shows that all these animals have descended from a common progenitor, and that the differences between them have been produced by subsequent modification. The rudimentary organs of organic beings are of the highest importance. Organs which are rudimentary in one species are often well developed in other species of the same class. The wings of the ostrich are rudimentary, but the wings of most other birds are well developed. The teeth of the whale are rudimentary, but the teeth of most other mammals are well developed. The tail of man is rudimentary, but the tail of most other mammals is well developed. All these facts are explained on the theory of descent with modification. They show that the ostrich has descended from a bird which had well-developed wings, that the whale has descended from an animal which had well-developed teeth, and that man has descended from an animal which had a well-developed tail. I have now recapitulated the main facts and considerations which have thoroughly convinced me that species have been modified during a long course of descent. I have given a brief abstract of the reasons which have led me to this conclusion. I have also given a brief abstract of the objections which have been urged against this conclusion. I have not been able to enter on details, but I believe that I have said enough to show that the theory of the descent of all the species of the same class from a common progenitor, with subsequent modification, is a theory which is supported by a vast body of evidence. This theory of descent with modification through variation and natural selection is the only one which can explain the great and striking facts of the geographical distribution, the geological succession, the mutual affinities, the embryological relations, and the rudimentary organs of organic beings. It is the only theory which can explain the fact that the species of the past are not the same as the species of the present, and that the species of the present are not the same in different parts of the world. It is the only theory which can explain the fact that the species of the same genus are more closely related to each other than are the species of different genera, and that the species of a genus can be grouped into subgenera and the species of a subgenus into lesser groups. It is the only theory which can explain the fact that the embryos of the most distinct species of the same class are often wonderfully like each other, and that the rudimentary organs of one species are often well developed in other species of the same class. I see no good reason why the views given in this volume should shock the religious feelings of anyone. It is satisfactory as showing how transient such impressions are, to remember that the greatest discovery ever made by man, namely the law of the attraction of gravity, was also attacked by Leibniz as subversive of natural and inferentially of revealed religion. A celebrated author and divine has written to me that he has gradually learnt to see that it is just as noble a conception of the deity to believe that he created a few original forms capable of self-development into other and needful forms, as to believe that he required a fresh act of creation to supply the voids caused by the action of his laws. Why, it may be asked, have all the most eminent living naturalists and geologists rejected this view of the mutability of species? It cannot be asserted that organic beings in a state of nature are subject to no variation. It cannot be proved that the amount of variation in the course of ages is a limited quantity. No clear distinction has been or can be drawn between species and well-marked varieties. It cannot be maintained that species when intercrossed are invariably sterile, and varieties invariably fertile, or that sterility is a special endowment and sign of creation. The belief that species were immutable productions was almost unavoidable as long as the history of the world was thought to be of short duration, and now that we have acquired some idea of the lapse of time, we are too apt to assume without proof that the geological record is so perfect that it would have afforded us plain evidence of the mutation of species if they had undergone mutation. But the chief cause of our natural unwillingness to admit that one species has given birth to other and distinct species is that we are always slow in admitting any great change of which we do not see the steps. The mind cannot possibly grasp the full meaning of the term of even 1,000,000 years. It cannot add up and perceive the full effects of many slight variations accumulated during an almost infinite number of generations. Although I am fully convinced of the truth of the views given in this volume under the form of an abstract, I by no means expect to convince experienced naturalists, whose minds are stocked with a multitude of facts all viewed during a long course of years, from a point of view directly opposite to mine. It is so easy to hide our ignorance under such expressions as the plan of creation, unity of design and see, and to think that we give an explanation when we only restate a fact. Anyone whose disposition leads him to attach more weight to unexplained difficulties than to the explanation of a certain number of facts will certainly reject the theory. But I look with confidence to the future, to young and rising naturalists who will be able to view both sides of the question with impartiality. Whoever is led to believe that species are mutable will do good service by conscientiously expressing his conviction, for thus only can the load of prejudice by which this subject is overwhelmed be removed. Several eminent naturalists have of late published their belief that a multitude of reputed species in each genus are not real species, but that other species are real, that is, have been independently created. This seems to me a strange conclusion to arrive at. They admit that a multitude of forms which till lately they themselves thought were special creations, and which are still thus looked at by the majority of naturalists, and which have all the external characteristic features of true species, they admit that these have been produced by variation, but they refuse to extend the same view to other and slightly different forms. Nevertheless, they do not pretend that they can define or even conjecture which are the created forms of life, and which are those produced by secondary laws. They admit variation as a vera causa in one case, they arbitrarily reject it in another, without assigning any distinction in the two cases. The day will come when this will be given as a curious illustration of the blindness of preconceived opinion. These authors seem no more startled at a miraculous act of creation than at an ordinary birth. But do they really believe that at innumerable periods in the Earth's history, certain elemental atoms have been commanded suddenly to flash into living tissues? Do they believe that at each supposed act of creation one individual or many were produced? Were all the infinitely numerous kinds of animals and plants created as eggs or seed, or as full-grown? And in the case of mammals, were they created bearing the false marks of nourishment from the mother's womb? Undoubtedly, some of these same questions cannot be answered by those who believe in the appearance or creation of only a few forms of life, or of some one form alone. It may be asked how far I extend the doctrine of the modification of species. The question is difficult to answer because the more distinct the forms are which we may consider, by so much the arguments in favour of community of descent become fewer in number and less in force. But some arguments of the greatest weight extend very far. All the members of whole classes are connected together by a chain of affinities, and all can be classed on the same principle, in groups subordinate to groups. Fossil remains sometimes tend to fill up very wide intervals between existing orders. Organs in a rudimentary condition plainly show that an early progenitor had the organ in a fully developed condition, and this in some cases implies wonderful changes in life. Throughout a whole class, various structures are formed on the same pattern, and at a very early age the embryos closely resemble each other. Therefore, I cannot doubt that the theory of descent with modification embraces all the members of the same great class or kingdom. I believe that animals are descended from at most only 4 or 5 progenitors, and plants from an equal or lesser number. Analogy would lead me one step further, namely to the belief that all animals and plants are descended from some one prototype. But an analogy may be a deceitful guide. Nevertheless, all living things have much in common in their chemical composition, their cellular structure, their laws of growth, and their liability to injurious influences. We see this even in so trifling a circumstance as that the same poison often similarly affects plants and animals, or that the poison secreted by the gallfly produces monstrous growths on the wild rose or oak tree. With all organic beings, sexual reproduction seems to be essentially similar. With all, as far as is at present known, the germinal vesicle is the same, so that all organisms start from a common origin. Therefore, I should infer from analogy that probably all the organic beings which have ever lived on this earth have descended from some one primordial form into which life was first breathed. But this inference is chiefly grounded on analogy, and it is immaterial whether or not it be accepted. No doubt it is possible, as Mr. G.H. Lew has urged, that at the first commencement of life many different forms were evolved, but if so, we may conclude that only a very few have left modified descendants. For, as I have recently remarked in regard to the members of each great class, such as the vertebrata, articulata, etc., we have distinct evidence in their embryological, homologous and rudimentary structures, that within each class all are descended from a single progenitor. When the views advanced by me in this volume and by Mr. Wallace, or when analogous views on the origin of species are generally admitted, we can dimly foresee that there will be a considerable revolution in natural history. Systematists will be able to pursue their labours as at present, but they will not be incessantly haunted by the shadowy doubt whether this or that form be a true species. This I feel sure, and I speak after experience, will be no slight relief. The endless disputes whether or not some 50 species of British plants are good species will cease. Systematists will have only to decide, not that this will be easy, whether any form be sufficiently constant and distinct from other forms to be capable of definition, and if definable, whether the differences be sufficiently important to deserve a specific name. This latter point will become a far more essential consideration than it is at present, for differences, however slight, between any two forms, if not blended by intermediate gradations, are looked on by most naturalists as sufficient to raise both forms to the rank of species. Hereafter we shall be compelled to acknowledge that the only distinction between species and well-marked varieties, that the latter are known or believed to be connected at the present day by intermediate gradations, whereas species were formerly thus connected. Hence, without rejecting the consideration of the present existence of intermediate gradations between any two forms, we shall be led to weigh more carefully and to value higher the actual amount of difference between them. It is quite possible that forms now generally acknowledged to be merely varieties may hereafter be thought worthy of specific names, and again that forms now ranked as species may be ranked as varieties. In the future I see open fields for far more important researches. Psychology will be based on a new foundation, that of the necessary acquirement of each mental power and capacity by gradation. Light will be thrown on the origin of man and his history. Authors of the highest eminence seem to be fully satisfied with the view that each species has been independently created. To my mind, it accords better with what we know of the laws impressed on matter by the Creator. that the production and extinction of the past and present inhabitants of the world should have been due to secondary causes, like those determining the birth and death of the individual. When I view all beings not as special creations, but as the lineal descendants of some few beings which lived long before the first bed of the Silurian system was deposited, they seem to me to become ennobled. Judging from the past, we may safely infer that not one living species will transmit its unaltered likeness to a distant futurity, and of the species now living very few will transmit progeny of any kind to a far distant futurity, for the manner in which all organic beings are grouped shows that the greater number of species in each genus and all the species in many genera have left no descendants but have become utterly extinct. We can so far take a prophetic glance into futurity as to foretell that it will be the common and widely spread species belonging to the larger and dominant groups within each class which will ultimately prevail and procreate new and dominant species. As all the living forms of life are the lineal descendants of those which lived long before the Silurian epoch, we may feel certain that the ordinary succession by generation has never once been broken, and that no cataclysm has desolated the whole world. Hence we may look with some confidence to a secure future of great length, and as natural selection works solely by and for the good of each being, all corporeal and mental endowments will tend to progress towards perfection. It is interesting to contemplate an entangled bank clothed with many plants of many kinds, with birds singing on the bushes, with various insects flitting about, and with worms crawling through the damp earth, and to reflect that these elaborately constructed forms, so different from each other, and dependent on each other in so complex a manner, have all been produced by laws acting around us. These laws, taken in the largest sense, being growth with reproduction, inheritance which is almost implied by reproduction, variability from the indirect and direct action of the external conditions of life, and from use and disuse, a ratio of increase so high as to lead to a struggle for life, and as a consequence to natural selection, entailing divergence of character and the extinction of less improved forms. Thus, from the war of nature, from famine and death, the most exalted object which we are capable of conceiving, namely the production of the higher animals, directly follows. There is grandeur in this view of life with its several powers, having been originally breathed into a few forms or into one, and that whilst this planet has gone cycling on according to the fixed law of gravity. From so simple a beginning, endless forms most beautiful and most wonderful have been, and are being evolved.